Yeah, okay. Right. Good morning and welcome to the third day of the course on design, packaging and life cycle engineering of electronic systems under the Gyan program of Ministry of HRD India, Government of India. My name is Anandaroop Bhattacharya, and today what I will be teaching, I am the host faculty and the coordinating faculty from IIT Kharagpur, as many of you may be knowing. Today I will be teaching the thermal aspects and the thermal module of this course. Okay. So, you have listened to Professor Abhijit Dasgupta. He has really enriched us with a lot of knowledge over the last 2 days, and we are, I think, at a stage where we know what an electronic packaging is, what are the different types of packages and so on. And I believe he has also made multiple references to the fact that when powered on, all these electronic devices generate a lot of heat, and it is important for us to come up with proper cooling as well as thermal management techniques, so that the heat can be dissipated and the temperatures are kept within their allowable thresholds. So, we are going to talk about those today. Before going, I would like to acknowledge my previous employer Intel, and some of you are here from my previous employment place. What I am going to teach today, or what I am going to show you today, a lot of it is taken from a course that me and some of my colleagues had developed while I was at Intel. So, some of it you may find familiar, and of course, I have tweaked, I have borrowed some of the materials from there. They are very basic materials, and then some of these are newer additions. Okay. But I want to acknowledge the help of all my colleagues who had at Intel, both at US and India. The way we will start is, we will start with some very basic heat transfer concepts, which for people with mechanical background may be a repetition of what you already know, but for people with non-mechanical background it may be a good brush up. Okay. After that, we will go to the concept of thermal resistance, then we will talk a little bit about the cooling techniques for microprocessors, and then we will discuss a few things about numerical modeling, how we do it and what is important, what is not important, and so on. And during this exercise, we will have it in a discussion mode, especially towards in the last two topics, where you can also tell me about your experiences and I can share my experiences, and let that be a two-way traffic. Now, let us start with a few words about the need for thermal management. This pie chart is a little dated, I would say about 7 to 8 years, but I think the basic message does not change. If you look at the various causes of failure of electronic packages and systems, this is what it comes out, and you see a major chunk of the pie is due to temperature, due to overheating, where the temperature of the device, of the die, of the CPU in case of computers exceeded the threshold limit and thereafter failed. And the reason for this overheating can be a lot of things, but final reason why it failed is the fact that it exceeded its allowable temperature. So, we need to keep the temperature within the limit, which means that we have to remove the heat that is generated, that is causing this temperature rise. So, let us start with some of the fundamentals of heat transfer, namely the three modes of heat transfer. Now, why does heat move from one place to another? Because of temperature difference, just like electric current flows due to voltage difference, we all know that. So, for any heat to flow, there has to be a temperature gradient. So, if I put two bodies at the same temperature next to each other, there will not be any resultant heat flow. Okay. Now, when we have a temperature gradient, then heat can be lost depending on the situation and the scenario and the boundary conditions. Heat can be primarily lost by three modes, which we probably all know from our high school physics: conduction, convection and radiation. So, in conduction, what happens is, we typically talk about conduction through a solid or a liquid or a gas also, but in liquid and a gas many a times there is also bulk movement of which results in convection as well. So, let us keep that discussion on the side for a while, and let us talk about just conduction. So, conduction typically happens because when the temperature goes up, the kinetic energy of the molecules rises, and then they start vibrating with higher energy, and this energy is then transferred in the next layer of molecules, so on and so forth, and that is how the energy is transferred from one end to the other, from the hotter end to the colder end. Now, for mostly for practical purposes, we engineers, what we do is we say, okay, let us take a slab like this, and let us say one face of that is at a hot temperature, the other face is at a cold temperature, then how much heat is going to flow? That is what we want to quantify, and that is given by this expression over here, as you see, Ka, the temperature difference delta T, over L, where L is the thickness. I am sorry, it has not come out in the slide. The L is the thickness of this slab, if I may call it so, that is the thickness through which the heat has to flow. Okay. Now, what is K? K is the thermal conductivity of that material, and let us consider it to be a solid as of now. So, K is the thermal conductivity of the solid, A is the cross sectional area through which the heat flows, and delta T over L, as I just discussed, delta T is the temperature difference between the hotter side and the colder side, and capital L over here is this length or the thickness through which the heat is flowing. So, electrical engineers can draw a ready reference or can draw an analogy with Q as the current and delta T as the voltage, right. There you have rho L over A, where rho is the resistivity. Here K is the conductivity, therefore, it goes to the numerator and it is L over Ka, right. But otherwise, it is very similar. Electric current flows due to voltage difference or potential difference, heat flows due to temperature difference. The next mode is convection. Now, convection is what we call in the thermofluids language, we say that it is conduction which is aided by advection or bulk flow of the fluid. But essentially, for practical purposes, what it means is it is not just transfer of energy due to vibration of molecules, atoms and electrons and phonons, but it is also due to bulk movement of the fluid. So, you need to have a fluid that can flow. So, in this case I am showing a very simple example of a slab or a plate which is at a hot temperature. So, let us say this phone is at a hot temperature and I place it in the ambient, okay, and I just place it like this, and we all know that over time it is going to cool down. Why would it cool down? Because there is a temperature difference between the hot surface and the ambient. And how will it cool down? How will the heat flow? The heat will flow because of convection. Now, convection can again be of two types, and we will come to that, but at this point let us say that this convection is because there is an air current or air stream. It can be water, it can be any fluid also, but let us consider it to be air, which is at a lower temperature flowing above this hot surface, and as it flows it takes away the heat. Therefore, the temperature at which the air comes in at this end will be lower, and what it exits at will be higher, right. I am telling in very basic terms. Okay. Now, how much is the heat that is going to be lost? Of course, the heat that is going to be lost is given by this expression H A delta T, where A is the area that is available for heat transfer. Okay. So, if it is a large surface area from which the heat is getting lost. Okay. H is known as the heat transfer coefficient, which by the way, if when people who are studying or basically doing research in convective heat transfer under various circumstances, etc., finally it just boils down to quantifying this parameter H under a certain under a certain situation, under a certain set of boundary conditions and geometry. How can I quantify this heat? How can I quantify and calculate the heat transfer coefficient? But for the time being, let us assume that H is known to us. So, therefore, how much heat will get lost because of this is H A delta T, where delta T is again the temperature of the plate or the hot surface minus the temperature of the ambient to which it is losing the heat. Okay. The last one is radiation, which is given by this expression. This is by the way a very simplified expression again, radiation. Q is epsilon A sigma if it is between two bodies at high and low temperature. The heat transfer actually, unlike conduction and convection, which is directly proportional to the temperature difference, this is proportional to the difference of the fourth power of their absolute temperatures. Okay. Again, I want to reiterate here, whenever we are doing any calculation regarding about radiation, the first thing that all of us must remember and do is convert the temperatures to absolute scale. For conduction convection it does not matter, because the difference is ultimately delta T. So, whether you do it in centigrade or whether you do it in absolute scale, delta T will remain the same, but in radiation it can lead to a lot of error. Okay. So, we must keep that in mind. Epsilon is known as the emissivity of the surface from where heat is getting emitted. A is again the cross sectional area, sigma is known as the Stefan Boltzmann constant, and it is a value equal to sigma equals to 5.67 into 10 to the power minus 8, and the units are going to be watt per meter squared per Kelvin to the power 4, right. Now, why I am showing this and showing this value is, look at this order of magnitude 10 to the power minus 8. So, therefore, for radiation heat or heat loss by radiation to be a significant value, the temperatures also have to, or at least the temperature difference has to be high enough. So, many a times let us say I am keeping a solid at a temperature of 50 degrees at an ambient of 30 degrees or so on, we will see that the radiation component is typically less. Okay. So, many a times we neglect radiation, especially when you have, let us say, convection because of movement of a stream of air or water. We will say, you know, the radiation component will be so small and negligible that we are not going to consider that. The primary reason for heat dissipation is going to be either conduction or convection, but that is an engineering judgment we have to take. Many a times if we neglect radiation, it can also lead to underestimation of heat dissipation. Okay. But I am just trying to mention that it is important to know and calculate a priori whether this radiation heat transfer can be significant or can it be neglected compared to the other modes of heat transfer which is available to you, all right. Okay. So, that is a one slide snapshot of a semester long course on heat transfer that I teach. Okay. No, okay, there is one more. So, I say convection can be of two types, one is natural convection, one is forced convection, all right. Natural convection is, let us say I take a hot surface, let us say this hot bowl of soup, and I leave it in the ambient. So, what happens? The air molecules in close contact with this hot liquid surface is going to get hot. As it gets hot, its density reduces, it gets lighter, and therefore, the hot air has to rise. As it rises, the cold air from the surroundings will come and take its place, in turn get again heated up and rise and so on. So, this is how the natural convection happens, which is driven by the density difference. So, we also call it natural convection. A more scientifically correct term is buoyancy induced flow. Because why? Because it is a buoyancy force that drives the air to, or air or the fluid to move up. Okay. Now, let us say this is not enough. Okay. It is cooling down, but cooling down too slowly. I need to have this soup. So, what will I do? This is what we do, right. Essentially, what are we doing? We are trying to give rise to an air current to flow over this hot surface. Okay. What we do normally by blowing air through our mouth, and what we do actually by putting a fan near a hot surface, essentially what we are trying to do is the same. We are trying to give rise to an air current which is going to forcibly remove and result in a bulk movement of the flow above the hot surface, and that is how the heat is going to be dissipated. It is not dependent on just the buoyancy difference, I am actually forcing it, and of course, I am therefore using external power, because if I am putting a fan, I have to power it up, okay, I have to supply energy. If it is water, I have to run it by a pump, or if it is a gas, I have to run it by a compressor, whatever it is, all right. But the heat transfer coefficient in natural convection as expected is low, heat transfer coefficient in forced convection is going to be high. Okay. But again, as I said, forced convection comes with at a penalty, where you have to actually have a prime mover like a fan or a pump, which you have to power up, for which you need electrical energy. Natural convection just comes to you for free. Many a times the word free convection is also used in many textbooks, you will see. Okay. All right. The next concept I am going to talk about is the concept of heat flux. Heat flux is the rate of heat transfer per unit area. So, many a times this parameter is of higher importance than the heat flow itself, because you know So, if you tell me from electronic packaging point of view itself, you say that I have a package and I have a die sitting on a substrate or a package, and that is dissipating 10 watts, can you cool it? And my first question is going to be, how big is the die? If you say it is 1 inch by 1 inch, I said okay, no brainer. If you say it is 0.5 centimeter, 5 millimeter by 5 millimeter, I say oh, that is going to be a challenge, we have to think about it. Okay. So, therefore, the heat transfer per unit area becomes important, the watt per meter squared or watt per centimeter squared. Okay. That sometimes is the more critical parameter that gives me a feel of how challenging the cooling problem is going to be. Okay. So, let us say I am talking consider silicon die in an IC package, the power is 25 watts, the area is 0.8 centimeter squared, all right. So, the heat flux through the die is going to be 31.25 watts per centimeter squared. Okay. This is just an example. And so, from this number I will go and then, so let us take again this example and I will do a little bit of more work here. So, let us say I take this and I will say Q double prime is told to me to be 31.25 watts per centimeter squared. Okay. Fair enough. Then I will ask you, okay, what is the maximum temperature of the die that you can withstand? And you say that Tj max, J stands for junction, we will come to those nomenclature, and you say 100 degrees. I said okay, fine. What is your ambient temperature, the local ambient? If I have to use air, what is the temperature of the surroundings? You will say okay, T ambient, maybe inside the system, maybe 35. Okay, fair enough. So, which means I have a delta T of 65 degrees centigrade, clear, all right. Now, my Q double prime is what? H times delta T, why? Because Q is H A delta T for convection, clear. So, if this is the case, then I will say okay, for the given scenario, therefore, my H has to be, H required will be Q double prime over delta T, and that comes out to be 31.25 divided by 35, or delta T is 65, sorry, divided by 65 watts per centimeter squared Kelvin. How much is it coming to? This is 32.5, it would have been exactly half,
approximately
0.45 or something, right? Yeah. Okay. So, 0.45 watts per centimeter squared Kelvin. So, per meter squared it will have to be multiplied by 10 to the power 4. So, that becomes 4.5 into 10 to the power 3, am I there? Okay. Watts per meter squared Kelvin. Okay. This, trust me, is an extremely high number. Okay. It is not easy. 4500 watts per meter squared Kelvin is not easy to get. Air cooling probably very difficult, right. Okay. So, this is just to give you a feel, and so this gives me a challenge. This is the kind of H I need to get. Okay. All right. This I think we just talked about. Now, if I just recast the conduction heat transfer equation into the heat flux equation, then Q double prime is K delta T over L, clear. And similarly, for convection we just talked about Q double prime is H delta T, clear. All right. So, this part, any questions so far? All right. So, next concept I want to introduce, and we will talk about it in more detail later, especially with respect to resistance networks, but what is a thermal resistance? Just like electrical resistance, we thermal engineers also come up with an equivalent resistance called a thermal resistance. Okay. So, it is shown over here, Q is K A delta T over L. If I rearrange it, it comes out to be like this. So, the conduction thermal resistance therefore is L over K A. Okay. So, actually this is a very powerful tool, as we will see later. It is a method that we often use to represent systems, electronic systems definitely, and it is analogous to electrical resistance, because as we see, you can see a direct correspondence with Ohm's law here, and probably a little more clear over here. Ohm's law, if you have voltage difference, you have an electrical resistance L over sigma A or rho L over A, and you have current that flows, and similarly over here you have a temperature difference, you have a heat or power that flows, which is in watts, and the conduction thermal resistance is L over K A. Clear? All right. Just like electrical resistance, in thermal resistance also, depending on the heat flow path, we can have resistances in series, we can have resistances in parallel. For example, let us say I have two blocks like this. This is one block, this is another block. Let us say this is A, this is B. This face is at a temperature T H, and this phase is at a temperature T C, H for hot, C for cold. So, definitely there is a temperature gradient, and therefore, heat is going to flow. Heat is going to flow in this direction. Now, the same heat is also going to flow through B. So, therefore, what do I have? I can write that the thermal resistance due to A will be L, this is L A, this is L B, L A over K A times A, because the cross sectional area is still the same for both, and R B similarly is going to be L B over K B times A. Now, since the same heat is going to flow through A and B, right, so we can say that these resistances are in series. Therefore, R equivalent is going to be R A plus R B. Okay. So, therefore, how much heat am I going to flow? Q is going to be T H minus T C divided by R equivalent, okay, or I can write T H minus T C divided by L A over K A A plus L B over K B B. Clear? However, if I just swap this and say I now have two blocks in this manner, this is A, this is B, okay, both have the same length. However, the cross sectional areas are now going to be different. And this is going to be A B. So, in this case, however, therefore, these two resistances are in parallel, because the heat that is going to come from here is now going to split into two. It is going to be split into Q A and Q B. So, this will be Q B, this will be Q A. Clear? So, therefore, my equivalent resistance is going to be 1 divided by 1 over R A plus 1 over R B, whereas R A is going to be L over K A of A, R B is going to be L of K B A of B. The total Q is going to be, again this whole face is at T H and this whole face is at T B T C. except that this equivalent resistance is now going to be different, and different amounts of heat are going to flow through A and B depending on their respective thermal resistances, right. And again, just like electric current tries to or tends to flow through the path of least resistance, heat also tends to flow through path of the least resistance. So, let us say if this is A is an insulator and B is a conductor, let us say plastic and copper, most of the heat is going to flow through B and very little through A. Okay. And if I want them to be close to each other, then I have to play around with the cross sectional area. The cross sectional area of the copper will be made much smaller, cross sectional area of the plastic or or insulating material has to be made much larger, so that the resistances are close to each other. Clear? All right. This is convection, I already talked about. By the way, that Q equals to H A delta T is also called Newton's law of cooling, and as I said, the challenge lies in determination of the heat transfer coefficient, okay, because that depends on boundary conditions, that depends on the surface geometry or even the entire embodiment how it is. It also depends on what fluid you are using and how the fluid is flowing. Okay. So, this is where the challenge lies, and I do not think I have a slide. So, let me just spend a couple of minutes on determination of H, which is heat transfer coefficient. How do we determine? Okay. It depends on a lot of conditions, as we said. Now, of course, people who are doing research or doing work in thermal fluid mechanics, heat transfer, they will of course depending on their geometry and whatever they are studying, they will spend time on coming up with these. But mostly the good news is, for most of us who just want to get an estimate, a lot of work has already been done over the last 100 years. Okay. So, typically what we have, if you look up the literature, you will have what is called Nusselt number correlations. Okay. Now, what is Nusselt number? Nusselt number is given by H, which is the heat transfer coefficient, times some length scale, let me write it as L for now, over K of the fluid, where L I will write as length scale and Kf is the fluid conductivity, fluid thermal conductivity. Okay. And this typically for force convection is a function of a couple of other non-dimensional parameters. By the way, Nusselt number, I forgot to mention, H L over K, if you just put the units, you will see that this comes out to be a non-dimensional number. Actually, they have all physical significances, I am not going to get into those details. And the correlations typically relate Nusselt number to other non-dimensional parameters. So, the first one I am going to write is Reynolds and Prandtl number. For force convection, this is what we will typically get, and the second one I am going to write is Grashof and Prandtl number, and I am going to explain in a minute what these are. Okay. Now, what is Reynolds number? Re is Reynolds number, typically given by rho, the velocity v, L, which is the length scale, over mu. Okay. Rho is the density, mu is viscosity, v is velocity, because I am talking about force convection. So, something must be moving with some velocity, all right. Okay, so, this is Reynolds number, I am sorry. What is Prandtl number? Mu Cp over Kf, Cp specific heat, mu I have already defined, Kf also is fluid conductivity I have defined. Okay. So, let us now look a little bit into this equation, function of Reynolds number. So, Nusselt number, which is a non-dimensional heat transfer coefficient, which kind of tells you how efficient your heat transfer is going to be. What does it depend on? It depends on the velocity, quite intuitive, right. If I have a hot surface being cooled by a stream of air, higher the velocity of the air, better will be the cooling. It is quite intuitive. Okay. It is going to be a function of viscosity, because the fluid cannot flow very freely. If the viscous force is trying to pull it back, then I am not going to be able to dissipate the thermal energy that efficiently. Okay. Density, that can play in both ways. One is if it is a heavier fluid, it also helps because for a given volume there is larger mass, so it can move more heat, but it can also hurt you the other way. Okay. And then Prandtl number also, you see that higher the thermal conductivity and the viscosity. Okay. What else? Last one, which is Grashof number. So, let us do a little bit of guesswork. What is it going to depend on? Grashof number is for natural convection, where I do not have a flow, so therefore, I do not have a velocity. The movement happens due to density difference. So, therefore, the Grashof number must be a function of density difference, that has to be captured over here, and the density difference is because of temperature difference. So, we have something called an approximation, Boussinesq approximation, where it says that a density difference is proportional to the temperature difference, and the proportionality constant is given by a term called beta, which is the volumetric coefficient of expansion. So, we write it as G beta delta T L cubed. Okay. Over nu squared, sorry. Okay. Okay, and nu is actually mu over alpha, mu over rho. So, the Grashof number actually goes as the cube of the length scale, L cubed, all right. But what am I going to see here is, therefore, you can see what is important is the heat transfer coefficient for natural convection actually depends on the temperature difference. Unlike forced convection, where there will be a heat transfer, whether you have a temperature difference or not, there will be a heat transfer, there will be a heat transfer coefficient, sorry. You may not have any heat transfer because it is H A delta T, right. You have some H, but if your delta T is 0, does not matter, you are not going to, your Q is going to be 0. So, for forced convection, this is independent of the temperature difference, but for natural convection, the heat transfer coefficient is also a function of delta T, and of course, the total heat transfer is again of another multiplier of delta T, again multiplied by delta T. So, therefore, you see that in natural convection, the temperature difference, the dependence on temperature difference is much more significant. Clear? All right. Now, the good news is we have these Nusselt number correlations. If you just go to any heat transfer book, you will see for flat plate, flow through channels, tubes, flow over spheres, cylinders. Okay. Even flat plate for natural convection, whether it is facing up, facing down, because natural convection you can imagine depends on gravity, right. So, the hot air has to flow up. Now, let us say if this is my hot surface, but I put it down, what happens? The hot air would like to rise, but it cannot because it is obstructed. So, it has to now go around and then find its way to move up in a plume and so on, right. So, the good news is all these correlations people have worked tirelessly and have provided this for us. Okay. The last note I want to make is this length scale L many a times is length L for a plate or a surface, flat surface I mean, diameter d for a cylinder or sphere. Okay. There is also something called hydraulic diameter for a channel or a tube. Okay. And I will not get into the details of what hydraulic diameter is. These are all standard formula and definitions available in any book, but it is very important for us. So, as for people who are practicing engineers, unless you are doing a lot of in depth research, that is different, but for practical engineers, when I am given a problem, the judgment comes with the main judgment comes from which correlation to choose. It is there, the knowledge is there, but I have a lot of tools. I need to know which tool is perfect for the application, the problem I am trying to solve. Okay. All right. So, for convection again similar, 1 over H A will be the temperature difference. If you just write it in that manner, as you can see, thermal resistance comes out to be 1 over H A. Clear? The radiation heat transfer is a little difficult. It is difficult to come up with a exact, I mean of course, you can come up with a definition of thermal resistance, but what you will see is that is also again a function of temperature, because the heat that is emitted and the heat that is absorbed is proportional to the fourth power of the temperature. That is the problem. You cannot just remove delta T and equate it as a potential difference for an equivalent electrical circuit. All right. So, this is the emissive power that is given by the Stefan-Boltzmann law. Here you see Stefan-Boltzmann constant. Okay. So, this is radiation heat transfer many a times. For many practical applications, especially for computing products and all, this turns out to be a small contributor. However, if you are really talking about high temperature electronics, or where you are working on something under extremely cold temperatures, so that when the temperature difference is high, the radiation also becomes important. We have to have that judgment as to when to consider, when to neglect. Okay. All right. So, that is a brush up of some of the fundamentals, the modes of heat transfer, how do we calculate heat transfer coefficients, rate of heat transfer, and so on. Any questions so far? All right. If not, let us go to thermal resistance for packages. Okay. We will start with a few nomenclature here, and then try to look at them in more depth. The thermal resistance often denoted by theta. Okay. So, theta x y. So, which is the thermal resistance from x to y. Okay. Now, what is x to y? What in the context of an electronic package, what is an x, what is a y? Okay. So, x and y can be anything, x or y, any of them can be ambient, in which case we will denote them as A. This is standard nomenclature that is used in the industry. Of course, depending on the company you work for, there may be a little difference from one organization to another, but these are pretty much the list of different temperatures that is considered. Ambient definitely where you are putting in. B is typically the PCB board, whether it is the motherboard, whether it is the package, depends on your configuration, whether the die is directly on board or whether it is on a package or a substrate, which in turn is connected to the motherboard. Right. Case. Now, what is case? We will come to that. So, hold on to this now for now. J is the junction. So, this typically is an internal temperature inside the die, inside the silicon. Okay.
So, inside each transistor or inside the normal die?
Good question. So, typically the maximum temperature, there can be multiple places of the or multiple junctions. Okay, it depends if you select a multi-core architecture, you have multiple junctions over there. So, it really depends on the hottest temperature that we try to design for, and we call that the TJ. It's sometimes difficult to measure, if you go to internally, but many a times some of the thermal test vehicles that were being passed around, some of the damaged ones that Intel let me take away or when I left from US actually. So, these are thermal test vehicles. These typically will have a power map inside, not much of circuitry, typically heaters, and then we will have some temperature sensors, okay, to measure the temperature in the silicon at the places where the heat flux is maximum. Okay. Because at the end of the day, typically when I say that my CPU die cannot exceed 100 degrees, I am really talking about the maximum temperature at the junction, okay. And I will come to that. Non-uniform temperature distribution is something most common, it is actually reality. You are never going to get a CPU die with the same temperature at every point, okay. And your deciding factor for the design is the maximum temperature. It does not matter if the rest of 90% of the die is cool, but if that one point exceeds your temperature, your thermal design has failed. Okay. L is used as lead, okay. If we were talking about single inline package, dual inline package, the leads coming out yesterday, right, the J lead, the Gulving lead. When those are the main paths of heat transfer, many a times we put thermocouples over there to see what is the temperature. Okay. P is thermal plate, we will come to that. S is heat sink. So, more or less these are the typical subscripts that you will find if you are working in the industry. There may be some more, in certain cases some of these may not be valid, but kind of an, I would say, overall an exhaustive list. Okay. What is theta xy? It is the thermal resistance from point x to point y. So, if I say theta jc, what is theta jc? The thermal resistance of the junction to the ambient. Clear? Okay. The assumption over here is when I say, okay, no, sorry, before that, in the practical problem, if I tell you that, you know, I will give you a problem where theta jc is, let us say, 5 degrees C per watt, okay. And then I tell you I am dissipating, my total Q is 30 watt, no, not 30 will be too much, let us say 15 watts, okay. Sorry, theta J A, I am sorry, theta J A is 5 degrees centigrade per watt, my Q is 15 watts, and I am telling you if T ambient is 25 degrees, find T J. What will we do? We will say, okay, T J minus T A must be equal to Q times theta J A, right. So, therefore, 15 into 5, 75 degrees C. So, therefore, my T J is going to be 75 plus 25 equals to 100 degrees C, okay. That is my answer. The problem is in this is the fact that the key assumption is the entire heat goes from junction to ambient, or in this case if I look at the slide, when I say theta x y, the assumption is the entire heat goes from x to y, which may not be the case, okay. So, this is a drawback of this method of theta J A, but if you do a calculation in this manner, okay, because out of 15 watts maybe only 75% goes from junction to ambient in the path I am talking about, the rest may be going into the motherboard. So, in that case I should not be multiplying by 15, I should be multiplying by whatever fraction of that 15 is going in the direction of junction to ambient.
How do you find out that?
So, it is difficult to find that out, okay. So, okay, since you asked, it is a good question. So, we have to then determine theta J A, let us call it as theta 1, and theta J 2 elsewhere, most probably it will be the motherboard, and let us call it theta 2.
There might be like multiple cases, right? So, it might be through the
It can be theta 3, theta 4, theta 5, all that. So, therefore, just like your electrical resistance is in parallel, your Q will get split to Q 1, Q 2, Q3 blah 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 blah, and these will be the proportion, they will be proportional to the thermal resistance that is being offered, or is inversely proportional to the thermal resistance. Okay. So, we will look at examples like that. So, hold on to your question for a while. Okay. Now, one thing, even though I think the electrical engineers may refute this, but many times practically we say that in the electrical world you do come up with perfect insulators. You may disagree, you will say no, there is always some little current that flows. I agree to that, but for all practical purposes, let us say if I take a piece of plastic or a Teflon or so, and I put a voltage on the other one end, I can probably safely touch the other side. Heat, unfortunately, there is nothing called a perfect insulator. Air itself, for example, air probably is the and of course vacuum, there is no vacuum again is not practically feasible, right. It is a concept. You can go to very low pressures, but not 0. Okay. For most practical purposes where we talk about air, is one of the worst conductors. So, by the way, let me take this opportunity, I talked about thermal conductivity. I will give you some numbers. If I talk about thermal conductivity, just to get you a feel, because as engineers we need to understand numbers, okay, practicing engineers. So, thermal conductivity for copper roughly 400 watts per meter Kelvin, aluminum around 200 watts per meter Kelvin. Actually, pure aluminum is 238, the alloys will be 200, 210, 180, but okay, ballpark numbers. This is what we need to remember. Okay. What is a bad thermal conductivator but a metal? Anybody?
So what's the question?
What is a bad metallic or which is a metal which is a bad thermal conductor among metals? Of course, there are lots of them, but anybody? Stainless steel. Okay. Stainless steel is at 14. Okay, before that let me write, because this is something important. Silicon 120, stainless steel very bad, okay, compared to metals 14. Okay. Air at room temperature 0.026. Okay. Water single digit of decimal. Okay. So, gives you a feel for that, why we do this, or what is a good conductor, what is a bad conductor, and so on. Okay. This also tells you why we have double glass windows. It is not the window.
How about ceramics? If typically not different ceramics.
Ceramics will be single digit, like 3, 4, 5, like that. All right. So,
I'm sorry, what on the and polymers?
polymers also, for example, FR4 can be from 0.2, 0.4. FR4 typically will be that. And now, when you have the wiring traces, right, then you have a KX, KY, KZ depending on.
Glass is this with the glass in place that you're talking about? The number you gave for FR4?
I think so, yeah. Okay. So, key to good thermal design is to understand where and how heat flows, and taking Tharang's question, if you have multiple paths, which is always the case, how do we understand where is the heat going, where is most of the heat going, and where can we neglect the heat dissipation and so on. Okay. So, let us take this. This is a package that you saw, plastic PGA. Let us consider. Okay. So, these are capacitors on the die side. This is a PGA, pins over here, a substrate. Okay. So, if I look at this example, what you see is this is the die, which is where the heat is generated. Now, I saw that on top there is a copper heat slug, which is, let us consider it is just a copper plate. On top of this I can put a heat sink, which is what I have shown here. Then what happens? One of my heat flow paths is conduction. So, pink is conduction. So, it is conduction from the die through this copper slug into the base of the heat sink, okay, and then loss by primarily convection, maybe a little bit of radiation which may be neglected. Okay. Is there any other path? Yeah, of course there is. this is another path. Okay. So, conduction through all these layers into the motherboard and from the motherboard into the ambient again. Now, you can readily appreciate the fact that this thermal resistance is going to be much higher compared to something through a copper, then to a heat sink, which will typically be aluminum or copper, versus something that goes through this substrate, then maybe an organic substrate into the motherboard, then through these pins into the socket, then into the motherboard. This is going to be much the thermal resistance is going to be much higher. Therefore, let us say if I am dissipating 10 watts, just to take a round number, probably 8 watts is going to go in this direction and only 2 watts will go in this direction. I am just giving you some numbers. Okay. It depends on the properties, the geometry and so on. And then let us say I tell you that I want to have even more heat that is getting dissipated from the, I want most of the heat to come to the top. Then I will do something with this heat sink, maybe I will put a very powerful fan, so that my heat transfer coefficient is so high that most of the heat, this is the preferential path and so on. Okay. If I have to draw a resistance network for this, it can be complicated, but it is doable. Okay. Tj is what is going to determine my thermal design. This is what I am trying to keep under control, and what is my anchor temperature is the ambient temperature. So, heat is going to try and flow from this hottest temperature by the second law of thermodynamics. It has to flow from the hottest temperature Tj to the coldest temperature that is available to me around, which is the minimum temperature I can get into, which is ambient. I cannot go subambient without spending additional power by second law of thermodynamics. So, therefore, all the heat that is generated will finally get into ambient, and it can get into ambient by multiple paths. The first one is through the heat sink, okay, through the slug plate, through the heat sink to the ambient, then through the junction to the substrate, through the socket to the motherboard, then to the ambient, and some other small paths also. Once it comes to the substrate, then maybe from the side walls it can get lost, from this surface, these are all exposed to ambient. Clear? All right. So, this is the thermal resistance network, and this is why I am showing this example is trying to tell you that it is important what I told you 2 slides back. Key to the good thermal design and experimentation is understand how and where heat flows and quantify it. Okay. So, this is the knowledge, or this is the judgment as engineers that we need to have, and we do not have to be thermal engineers or electrical engineers to know this. This is just from our intuition and engineering knowledge, we can come up with these. Now, how to calculate these thermal resistances, etc.? Yes, there we need some heat transfer knowledge. Okay, not pretty elementary ones. Okay, any questions? Okay, before that, I have some additional slide called additional materials. Let us do a quick exercise on this one. Okay, let us try to do this. Maybe this is a small exercise we will all do together. What I am showing is I have a silicon die, thermal conductivity is given 120 watts per meter Kelvin. The dimensions are given, it is 500 microns or 0.5 mm thickness, 15 mm by 15 mm cross section, and then I have a copper plate on top, thermal conductivity 400, dimensions again 5 mm thick and 50 millimeters by 50 millimeters. Now, one thing I want to tell you over here is, and we will again discuss it later, is again as Professor Dasgupta was saying, even surfaces that appear very flat, absolutely polished, but they have a lot of these surface roughness if you go into the micro scale. Now, when you put these two surfaces together, what happens? There will be air voids, has to be, cannot be a perfect contact. We cannot eliminate that, but air is one of the worst thermal conductors, as you see. It is going to give rise to a lot of thermal resistance. It is a resistance to the heat flow path, it is going to block heat flow. Unfortunately, we cannot eliminate, but we can try to minimize. So, therefore, we want to replace the air or the voids, air in those voids, by something which is more conductive, and that is called a thermal interface material. A most common example is grease. Okay, there are thermal greases that are available, okay, and typically polymers with some filler materials inside. So, you will put a grease over there and try to fill in those voids. So that now you do not have air gap, you have those gaps filled in with something which has slightly higher thermal conductivity, 1 watts per meter Kelvin, not great, it is pretty low, but compare that to air 0.026, yeah, it is wonderful, right. I just increased it by 50 times. All right. So that is TIM is thermal interface materials, and on that top of that is a copper plate, and then I am flowing air at a temperature 30 degrees centigrade, and it is flowing such that the heat transfer coefficient has been calculated to be 60 watts per meter squared Kelvin. Okay. Just a side note, the heat transfer coefficient is given to you, in many cases it may not be given. So what you will do is, you will go to the standard Nusselt number correlation for flow over a flat plate, use these dimensions and calculate what is H. Clear? All right. It is a very simple problem. Let us try to assume that the heat flow is only in one direction, from the die through the TIM, through this copper plate, then to the ambient. Can we determine, given all these conditions, what is going to be the junction temperature at this die? Okay. That is our task. So, first thing, I am not showing any other path over here. So, what is the color that they have used? Blue for the die. Okay. So, this is my silicon. Then I have a small layer of thermal interface material TIM, then the copper plate, and then air flowing at the top. So, this is my junction temperature Tj, sorry, this is my ambient temperature Ta. Let me write that. Tj, my hottest temperature is Tj, my coldest temperature is Ta. How is the heat going to flow? I am told that there is a total of Q equals to 10 watts that is flowing from the silicon to the ambient. What will I do? I know that this heat is first going to flow through the silicon, then through the TIM, then through this copper plate, and then to the ambient, same heat. So, therefore, and each of these blocks or materials is going to have its own thermal resistance, is going to oppose the flow of heat through it, correct. Now, these resistances are all in series. So, what I will do is, how many resistances can I draw? So, the first one is R silicon, R TIM, R copper plate, and finally R convection, right. Now, for all of these are all conduction resistances, it is L over Ka, okay. But this one is going to be 1 over Ha, all right. Again, the cross sectional areas are the planar cross sectional area for all these cases, because that is the heat is flowing normal to that area, right. So, for the silicon they are all going to be different, by the way. For the silicon and the TIM it is going to be 15 mm by 15 mm, for the copper it is going to be 50 by 50, and also for convection it is going to be 50 by 50, right. And these are all, by the way, they will all be the equivalent L over Kas for each of these materials. So, what we will do is, if I do that, this is what I get. Okay, I have drawn it here I have drawn it the other way. So, the silicon resistance is coming out to be 0.02 degree C per watt or Kelvin per watt. The TIM is 0.22. The thermal plate or the copper plate is 0.005. Not surprising, right? Copper is one of the best conductors. It is relatively thick if you consider 5 mm. So, definitely it presents the least resistance. And finally, convection 6.67 or 66 degree C per watt. Clear? So, now if you take all of these, the rest is similar, the rest is simple, as we know, theta Ja Tj equal to Ta plus theta G, all this stuff. So, the total junction to ambient resistance, thermal resistance, which will be a summation of these individual ones, because they are all in series, is 6.9 degree C per watt, and the ambient was given to be 30 degrees, I believe, yeah, 30 degrees. So, therefore, my total junction temperature comes out to be 99 degrees centigrade. Clear?
Is this a worst case, or are we looking at the worst case, or are we looking at the average case? I mean, ambient is again a variant, right?
Right. So, for example, Intel assumes that the ambient is 35 degrees centigrade, that is what I have to design for. Okay. But however, if you are, for example, talking about hot and harsh like downhole electronics or military applications in a desert and so on, I have to assume the ambient to be something. Okay. Let us say I have to assume it to be 45 or 50. So, in that case, yes, if your threshold so this is 99 less than 100, and I say okay, fine. But if you say that no, the junction temperature has to be within 100, then I will say, boss, if you are operating somewhere at 50 degrees, you cannot run it at 10 watts. You have to reduce it, because otherwise you are going to fry your chip, or you are going to overheat the chip. So, this is how we do it normally. I will come to that. Worst case, there is also there is a steady state versus transient. I will come to that maybe after the break. And but these are all what I am. This is all assuming that the chip is always dissipating 10 watts throughout, no variations, nothing, and these are the maximum temperatures that we have. Under such a situations, which is kind of a worst case scenario, I would say, this is what it is.
So suppose like heat is transferred, so which heat transfer can be neglected, or whether
no here.
So whatever goes through a lead to the PCB, so whether it can be neglected or it has to be taken care.
It will all help. So, let us say you are okay, good question. So, let us go back to the previous slide. Okay. Now, before that, let me just make a final remark. Now, if you look at it, and this is again as a thermal designer, we need to have this judgment. I came up with this resistance stack, as we call it, resistance network, looked at the individual components and got some values. Now, this should tell us that what is the bottleneck. I want to increase the amount of power, given that my Tj is restricted to 100 degrees and I am already at 99, and I as a thermal engineer is pushing you back, the electrical engineers are saying, sorry, not more than 10 watts, and you are saying, come on, 10 watts I can do nothing, I have to put all these features and functionalities, and you must at least give me 15. I said, okay, 15. So, if I have to make this 15, then my theta Ja has to be reduced, okay. And theta J, to reduce theta Ja, I have to look at all these components. Now, if I look at this one as thermal engineer, I would say, where should I focus my attention on? If somebody comes and says, oh, copper, oh come on, they have been using it for so many years, now it is the age of graphite, pyrolytic graphite, 400 I can give you 1000, okay. Or diamond, sorry, what am I doing? I am already at 0.005. This is nothing, this is not contributing anything, even if you halve it, okay, even if you make it 0.0025, what is it going to change here? So, I would say, sorry, I know you have a good technology, but that is not going to solve my problem, that is not my bottleneck. I am going to focus on two areas. Can you tell me ways by which I can improve my convection heat transfer, thereby reduce this? And second, can you give me a better thermal interface material? If I can make this like 0.22 to 0.1, okay, 6.9 becomes 6.78, okay. So, that is where we have to focus, but finally, I am going to focus my attention on, how to improve this case to ambient thermal resistance, how to improve that, rather reduce that. That should be my focus as thermal engineers, not on something which is not going to give me a lot of return on investment. Okay. All right.
So that means what is your call is to reduce your ambient temperature at the particular location.
Or come up with a better heat. Ambient temperature is many a times not in your control.
No, what I'm saying is, see, ambient temperature is the temperature which lies around the
Correct.
particular point, right? So consider that my die is sitting in a laptop or something. In that location is the ambient which is created within that area of the die or the CPU. So you're going to control that ambient. Correct. That means I can put it in another way. I'm
No.
going to control my ambient.
Possible. That's a very good point you raise. Maybe today afternoon I am going to talk about some other thermal technologies, and I will hit upon your point. But right now, just to give an answer to you, is many a times that ambient is not something I can really control. It is dictated by the surroundings, right? If I am in this room, maybe fine. If I go outdoors, okay. For example, I started my career in Intel Arizona. In the month of May, many times you would go out, and that time you would sit outside and work on the computers. You could feel the fan is really running. Oh, it's really giving all its effort to keep the temperature down. Okay. So, but it is possible to control at a cost, and we will talk about that when we talk about thermal technologies. Okay. Now, coming to your point, Tarang, is in this example, if we talk about an equivalent example, is we just spoke about these resistances. Okay, we did not even consider this spreading and so on, but that is okay. We completely neglected this part, but there will be some heat transfer through this, and I should be able to calculate all of these also. Okay. And maybe it turns out that that was 6.9, this may come out to be like 25, right. So, then I would say 6.9 versus, or let us make it 28 and 7, let us say. So, which means this is 4 times the thermal resistance from junction to board, and then or through this path junction to board to ambient. The thermal resistance is 4 times compared to junction to heat sink to ambient. So, therefore, only 1/5 of my heat that is generated is going to flow through this, and 4/5 is going to flow through this. By the way, that is not negligible, by the way, 20% is not negligible. So, therefore, what I will do, and this is what I was talking about before, a drawback of the thermal resistance method is, look, I assume the entire heat is flowing in this direction, but it may turn out by the example that I just talked, just the numbers that I picked, that out of, it is not 10, actually it is 8 watts that is flowing through in this direction. Okay, fair enough. So, I should multiply this by 8, and that gives me a little bit of headroom. Or in other words, I would say, 10 watts is the limit of the heat that comes to the top, which is 80% of the total. Okay, so 10 by 0.8 is the amount of heat that you can put in. Okay.
If like 10 watts is, 8 watts is going up, that means 2 watts is going down.
Going down.
So that means like 2 watts might create some issue for the traces of the vias, right? So whatever.
It can be, it is possible. Yes. So, I am not even talking of this, of these intermediate temperatures, right. You can then, now that you know what is the total Q that is going through, and you know these thermal resistances, you can also calculate these intermediate temperatures. I am not even talking about those. Yes.
So is there a like way that like almost like some 90 to 90%, 95, like 99% can be taken?
That's what we try. That's what we try normally.
Okay.
Okay. And whatever we don't, we say that is extra. If something is getting lost from the other sides, it is an extra. Okay. I am not going to depend on that. And many a times, especially for pin grid array and all, where the socket is plastic with some etc., it's the thermal resistance to the board is very, very high. Okay. So, let us see, is this a good point to take a break? Yeah, maybe. Okay, maybe one more example. Let us look at this one, and this is the other extreme. The previous one was kind of a flip chip that Professor Dasgupta was talking about. The back side of the die was available, and I could put a copper plate and a heat sink on top. This one is an encapsulated die. A tape carrier package is what it is called. The die is encapsulated. You have thermal vias through your organic substrate, And then on the other side of the motherboard is what I have some free surface. I can put a thermal plane and a heat sink with a thermal grease or the thermal interface material, etc. Right. So, in this case, however, my primary heat flow path is going to be in the downward direction, because on top I have an encapsulant which is a poor conductor of heat. I will have something, and I will also have something that flows through this lead into the, this is a Gullwing lead, into this, and then back to the motherboard, and something from this surface to the ambient, and so on. So, now I am not, I had initially thought I will ask you to, we can do this exercise, but I think we have a fair understanding of what it happens. If I now have to look at what is the heat flow path, and if I have to construct a thermal resistance network, then we can do that. If this is the die temperature, path number 1, it is going to come through this adhesive into this thermal vias, through this plane, through this thermal grease to the heat sink and to the ambient. That is one path. Okay, some of it will go and then come into the motherboard, and then from the motherboard surface itself will get dissipated to the ambient, probably a smaller fraction, but something. Okay. Part of it will go up through the encapsulant into the ambient, part of it will go through this connection into the leads, into the motherboard and back to the ambient, part of it will go directly from the lead to the motherboard. So, all these have to be considered. Okay. And this is where our engineering judgment comes into picture. This, and now doing a hand calculation, complete analysis can be cumbersome. It is possible, it is not difficult, but it is cumbersome, prone to error. So, many a times just by looking at it, we say that I think most of the heat is going to flow through this path. So, that is what I am going to talk about, and whatever flows through the other ones, those are extra. Okay. I am not going to depend on that. If my thermal design comes out that I am just missing out by 1 degree or 2 degree, then I am going to focus on this and say that if this 1 degree, 2 degree, will it help me? Can it be just can that shortfall be met by these alternate heat paths? If so, fine. Otherwise, if I am really falling short, I have to increase my heat dissipation by another 20% or so. I would better look at a better thermal interface material, a better heat sink, or something. I would like to try to improve this thermal path, the major thermal flow path. Okay. All right. So, let us take a break here. It is 11 o'clock by that clock, and when we come back, we will continue on this. Okay. So, देखियो नहीं हमें उसको start. Sure. Okay, welcome back after the break. So, I would just like to point out one more thing over here. We will see that later as well. When we talk about a configuration, let us say like this, where the area is changing. So, at the silicon level and the tin level, it was 15 mm by 15 mm. At the copper level, it became 50 by 50. Okay. So, there is a sudden expansion in the surface area normal to the heat flow path, or the direction normal to the direction of the heat flow. So, in such a case, we did a very simple analysis where the thermal plate was also taken as L over Ka for the copper plate. But actually what happens is, just to give you an analogy, for example, if you think of water flow through a pipe, you have a thin pipe and then suddenly there is a junction and the diameter of the pipe increases. Then what happens if you, especially people who have studied fluid mechanics, have a thin pipe and then suddenly there is a water that is flowing, then what happens? The water flows like this, and then it actually goes like this, right. So, the water has to kind of fan out, it has to spread. So, similarly, same thing when you have two materials. So, this is one block, this is another block. So, if I look at my heat flow lines, heat flux lines, it will flow parallelly through this, but after that what happens is, it is going to take some time So, this is spreading. So, what does it mean? It means that the entire heat throughout this thickness does not flow through the full surface area that is available, right. For some distance it cannot utilize the entire surface area that is available to itself, to it, or that this block offers, because it needs some thickness before it can spread out fully and then get conducted in a one dimensional direction, okay, only in one direction. So, there is some lateral spreading towards the beginning, and so this part therefore offers an additional resistance, thermal resistance, and this is called the spreading resistance. Okay. And so, what should we do here? When we talk about our copper, truly speaking, this portion, if I zoom it out, will actually have a spreading resistance followed by your L over K A. So, this is R conduction and this is R spreading. So, there is an additional resistance. Okay. So, this 6.9 does not include that, and depending on what is the thickness of this copper, it may not be negligible. Okay. If this is very thin, if the copper plate is very thin, it may so happen that the heat does not get enough thickness to spread out completely, and therefore, what you will see over here is, if you take a temperature contour on the top surface, you are going to see a central area of higher temperature surrounded by a peripheral area of lower temperature. Okay. Just like this pipe example I am talking about, if you put your hand very close, you are going to feel a stronger jet at the center and a weaker jet on the sides. If you move your hand further down, then probably the force of the water that will strike your hand will be more or less uniform across the entire surface, entire cross sectional area. Same thing over here. So, heat and the fluid flow and heat flow many a time in many ways are very analogous. Okay. Fluid flows due to pressure difference, you have volume flow rate and pressure difference, and here you have temperature difference and heat.
And you have the same current crowding in electrical.
Yes, exactly, right. You will also see that the potential, maybe as just a side note, it turns out that the potential that drives the flow times the flow is energy, voltage times current, clear, temperature difference times your pressure drop times volume flow rate. Okay. Over here it is a little different, because the flow itself is the energy, which is Q. All right. Even in solid mechanics also, force times displacement, or stress times strain is the specific energy. Okay. So, let us go back to the other one now and talk about some nomenclatures. View full screen. All right. Now, these are two common thermal architectures. Let me see, I think I have the, from yesterday, the props that I got, I have these two examples. Okay. The first one is called the bare die attach. Why bare die? If I look at it, this is a silicon which is in blue, and probably it is BGA attached to the substrate with an underfill epoxy, as you can see this over here between the solder balls. Then this is your organic substrate, and then again a ball grid array, and these balls will be bonded to the corresponding pads in the motherboard. Clear? What is on the other side? The silicon is just present like this, and to dissipate the heat from this, what we call the back side of the die, because this is a flip chip, I am going to put a heat sink on top as shown here, and then to reduce this interface resistance, I will put a thermal interface material. So, this many a times is called a bare die attach. Why? Because bare, because this die is exposed and the attachment of the heat sink or the thermal solution to the silicon is directly on the die. Clear? So, this is the interface. Now, what happens is a company like Intel or AMD who makes these processors is going to sell the package with the bare die to the OEM, which is the Dells and HPs of the world. Okay. Dell, HP, Toshiba, whoever makes the final computer, the system. And then this is that Dell and HP or Lenovo or these companies who are going to attach the thermal solution and control what is the thermal interface material that goes and so on and so forth. The decision is not on the semiconductor manufacturer, but on the final equipment manufacturer. Okay. So, as Intel or AMD, they may give suggestions, they may give guidance, this is a good thermal interface material that we have characterized, we have developed, which is good for our product, and this is what we want you to use, but finally whether they will use it or not, the decision is theirs. Okay. Okay. All right. So, this is often called the thermal interface material. I am calling it the first interface. Why? Because this is directly connected to the silicon. Now, there is another architecture where you have the silicon and then you have, typically it is mostly copper, coated copper, a plate on top. Okay. This you would have seen yesterday when Professor Dasgupta was showing some pictures, you would have seen the word lid in many cases. Okay. It is also called lid, it is also called integrated heat spreader or IHS. Okay. Lid, why? Because it kind of protects the package, so that is one function. Heat spreader, why? Because this is metal, and what happens is, because this is a good conductor, it will help you spread the heat. So, if 10 watts is coming through here, it is going to now spread it out so that it is dissipated over a larger surface area, and thereby your local heat fluxes come down. Heat flux is flux per unit area, right. So, it also acts as an integrated heat spreader. So, for a thermal engineer, I would rather prefer to use the word IHS or integrated heat spreader, because that is the primary function I am interested in. Of course, it also does other functions. So, if you now look at this package, this is a second type. What you do not see the bare silicon die over here, what you see is this plate, which is the heat spreader or the lid, right. This is actually copper of some thickness, it will be 2 mm, 3 mm, I think 1.5 and 3 were the standards, and on top of that it is coated, because copper gets oxidized and tarnished very often, very soon. All right. So, here also what happens is the semiconductor manufacturer controls. So, now what is sold by the semiconductor like the Intels and AMDs is a package in this manner, which also has the lid or integrated heat spreader. So, therefore, the first level of interface between the silicon and the heat spreader is controlled by the semiconductor manufacturer. The second level, where the heat sink comes on this heat spreader, is controlled by the equipment manufacturer. All right. So, this is many a times for this type of package, this is called TIM 1 and this is called TIM 2, thermal interface material 1, this thermal interface material 2. For this one, do you call it TIM 1 or TIM 2? I think both are used pretty often, and both are okay. TIM 2 if you consider it, if you look at it from the heat sink side, TIM 1 if you look at it from this, because there is only one level of interface here. Okay. Now, if I look at again the understanding the heat transfer paths, what happens here, this is how it is. Here there is further spreading over here, and then it goes into this, into the heat sink, right. All right. Again, I am neglecting the heat loss through the substrate into the motherboard and so on, which will have a little bit of effect. If I want to draw a thermal resistance network, this is what I am going to take. What are the temperatures? Now, let us look at the nomenclature. Tj, the junction, Ts, the heat sink, this is at the heat sink base, and Ta, the ambient. So, therefore, the thermal resistance network has two components, theta junction to sink, sink to ambient. Sink to ambient definitely will be controlled by what kind of convection, natural or forced, if it is forced, whether it is liquid or air, what is the geometry of the heat sink, so on and so forth. Yeah. Right. So, the theta junction to sink actually takes care of the TIM. Okay. Now, why am I saying all this? Because many a times when we characterize, when we do testing, then what happens is, where is it that I can attach a thermocouple or a temperature sensor? The junction, many a times it is already inbuilt. When we build the test vehicle, we already put it in, whether it is an RTD or a thermistor, whatever it is. The thermocouple, I can put it on the, on the bottom side of the heat sink base. I will make a groove and put the thermocouple so that I can measure the temperature. This thermal interface material typically is like 50 microns. I cannot put my thermocouple bead is thicker than that. I cannot measure the intermediate temperature of a thermocouple of a thermal interface material, right. But however, if I make these two measurements, the junction and the sink, or even at the top of the sink also, and I am trying out different interface materials, I should be able to at least compare and see which thermal interface material is good or bad. Granted that the thermal resistance that I measure has components, has contributions from the silicon, from the base of the heat sink and so on, but okay, but these are going to be there. So, if I see a reduction by an X amount, that must be due to the interface material, a little bit give and take, a little bit here and there. Okay. All right. By the way, these are all thetas, not psis. Okay. Please make that correction in your notes, or make a note in your notes so that you, when you refer to the slides, these are thetas. Okay. So, here now when you have a package like this with an integrated heat spreader, then there are a few other, you have first of all two thermal interface materials. What is it that what are the different temperatures we are concerned about? Theta junction Tj, Tc is theta case, which is on top of this. Okay. Then Ts, the heat sink, and ambient. Why? Because I have a junction to case which includes the resistance to the silicon, the resistance to the first interface material, and a little bit of resistance and the resistance through this integrated heat spreader, which by the way is the conduction resistance plus the spreading resistance in light of the discussion we just had. Then sink to case, case to sink, we can have a temperature at the base of the heat sink and at the top of the case, and that is going to give you a measure of the thermal TIM2 resistance, or the second thermal interface material resistance. Okay. So, this theta Cs will give you a fair bit of idea of how good your second level of interface material is. And then finally, as before, sink to ambient. Clear? Okay. The last note I want to mention is, most of the times, since the processor is sold along, for the second part I am talking about, since the processor is sold along with the integrated heat spreader, this interface material typically is silicon, is solder. Okay. Because solder is of course a very good conductor, this is the back side of the die, so there is no danger of shorting or anything, and the fact is typically when your processor goes bad, you just throw this package away. Okay. We normally do not go into this and try to rework this TIM and so on. So, I can have solder which kind of is permanent attached, even though some people may argue that solder is also reworkable, you can heat and remove it and all, but for most practical purposes we consider solder to be a permanent attach. Once you bond two surfaces by solder as an interface material, the intention is that, or the desire is that we will never have to take them apart again. On the other hand, if you are putting a heat sink, typically we would like the second level of interface, this one, or in this for a bare die the first level of interface, to be a reworkable material. So, that is why many a times a solder is not used. The most commonly what is being used, even though there are many other types of materials that we have also looked at, but what is typically used is a thermal grease or some kind of a gel with filler particles which are conductive, or something called phase change material. You can think of it as a polymer which melts at a certain temperature. So, it will come to you as a soft soft sheet of material, okay, like like a dough with like a thin layer of dough. Okay. You can cut it, take a small piece of the area equal to that of the die, put it on top and put the heat sink. When you power on the die, the material is such that it melts at a temperature, let us say 45 degrees for example. So, of course, your die is going to go at a higher temperature, at a temperature higher than 45. So, this material is going to melt, but it is very viscous. Okay. Since it is so viscous, but it melts, it becomes this a little fluidic state. It is in a fluid state, but it is still it will not flow out because it is very viscous, but it is the viscosity is good enough or low enough so that it can just flow and fill in all the voids. So, next time when you switch it off, the material had already percolated into the pores and filled up the voids. Okay. Next time you switch it on again it melts, but remains in that mushy state, thick enough so that it does not flow out, but still fluid enough so that the voids are all filled in. Okay. And then what we do is in the phase change materials we put in several types of filler materials and so on to increase its thermal conductivity, because by themselves these polymers are not good conductors. Think of organic polymers like wax, not good conductors. All right. So, advantages and disadvantages of theta measurement is thermal resistance. You see, it is a powerful tool, especially when we talk about thermal resistance networks. It helps us first to do some initial calculations. It helps us to kind of get a judgment of what is the primary heat flow path, what is the main path through which heat is going to flow, what are the other residual paths through which heat is also going to flow, and so on. And so, you can do some very quick calculations and compact thermal models. Detailed thermal models, of course, you have to go into a CFD software and do everything, but for small lumped type of modeling you can use resistance network. Disadvantages is, how do you determine these thermal resistances? Okay. So, one is through just calculations of L over Ka, there are correlations for spreading resistance, contact resistance and so on, we can do that. The other is through measurements, and in industry typically the calculations are going to give you an estimate, but if you have to certify a product you have to actually measure, and these measurements are not easy. Putting a thermocouple over here and making sure that the positions and the sizes are such that the heat flow path itself is not impacted. Remember, these thermocouples, when you introduce, these are obstructions to the heat flow path. That itself, the very introduction of these thermocouples is going to disturb the heat flow path. So, you have to be very careful as to where you are putting it and have an estimate of how much you are disturbing the heat flow path otherwise. So, these measurements are not easy. Okay. Putting a thermocouple on the case and on the sink, very difficult when you have just a 550 microns separating it, and that too of a greasy material. But so that is a disadvantage, and very sensitive to measurement error, definitely, especially now when we are trying to bring down all these resistances to like second place of decimal, except the heat sink to ambient. Then a little bit of temperature difference measurement here and there is going to impact quite significantly. Okay. All right, any questions? Let me see, in additional materials do I have anything else? No. Okay. This is another example exercise, but this is very simple. The junction to sink resistance is given, junction to sink mind you, not case, just the sink. Power dissipation 15 watts, 1.5. Maximum allowed junction temperature is designed to be 100 degrees centigrade. Okay. So, what is the sink temperature? Easy, right? You can quickly do that. Tj minus T sink is going to be Q times theta junction to sink. Q is given as 15 watts, this is given as 1.5 degrees C per watt. How much is it? 22.5. So, therefore, this is 22.5 degrees C. Therefore, the sink temperature is going to be Tj minus 22.5, which is 77.5, because Tj is given as 100 degrees C. Yeah, simple calculations that we do, that is all. Okay. So, now let us look at some of the common techniques of cooling of microprocessors. In the second half, we will talk about it will be more of a research presentation, where I am going to talk about some of the more modern and some of the newer techniques that have been looked at over the last 10 years or so. But these are some of the age old techniques and very reliable. You will find these only in probably 80 to 90% of the computers that you use. What are these? So, let us look at the thermal solution hierarchy. What is the cooling that you need to do as a thermal engineer? There are different levels. One is at the silicon level. Many a times I will show you some technologies in the second half, where we are trying to cool down the junction at the silicon level itself. How can we do that? I mean, it is not like I am letting the heat come out, I am trying to do something at the silicon level itself. Okay. Thin film thermoelectrics is one of them I am going to talk about. At the package level, what is it that I can do? And many a times this interface materials, etc., I would say these are package level. Okay. So, on the package itself we put the thermal solution, okay, which I am going to talk about can be a heat sink. Primarily you will find in most of your desktops and servers you will have heat sinks. Servers also have some liquid cooling, and in laptops you have what is called a heat pipe, which is, by the way, essentially a heat sink and nothing more than that. Okay. I will come to that, why I am telling. And then when you come to the system level, apart from the CPU and the die only, you may have, or rather you will have, several other challenges to take care of. Okay. We will talk about that. And so, it is no longer a CPU centric cooling. So, maybe 15 years back, when Moore's law was being followed and the CPU power was doubling every 12 to 18 months, the entire focus of thermal designers was on the CPU. The other things, memory, etc., will be, it is not a big deal, it will get cooled. But now what has happened is, first of all, because of architectural change, it is no longer what is the power, but it is performance per watt. That is what we are talking about. Okay. So, the powers are not going up, the CPU powers are not going up at the same level. In fact, there is a lot of focus on low power architecture, and the CPU powers are actually, for the same functionality, are actually coming down. Okay. So, on the other hand, the other functionalities and features in the system are going up. We now want everything to be done through our laptops and tablets and cell phones, right. I want high, I want a very powerful Wi-Fi, I want a lot of power, I want a lot of memory, I want 3D 4K graphics. So, these are all so therefore, these all require powerful devices at their own levels. So, memory is no longer like 1 watt, 2 watts. So, what do I do with that? Okay. So, therefore, we have to now focus on those other non CPU components as well, and then we will see for handheld products or laptops, which is also handheld, or you put it on your, where you come in, actually human actually comes in physical contact. You also need to take care of the outside temperatures. You do not want to touch something and burn your skin. You have to take care of noise levels. I can cool anything if you allow me to put a big fan, like you have a chimney exhaust. You cannot do that. You do not want a noisy computer sitting next to you. So, we will talk about all these. These are system level challenges. Okay. So, desktop systems traditionally have had heat sinks and fans. Okay. If you open a desktop, if you have a desktop in your room, you can go and open it. It is very easy to open a desktop. By the way, make sure it is already beyond warranty. Otherwise, if you open it and something goes wrong, your manufacturer is going to refuse to service it because you opened it yourself. But if it is beyond warranty, go ahead, nothing happens. Take off the chassis, you will see all these fans and heat sinks. Most likely you will find all these, especially in our country, actually even in US also, you will find most of the fans and heat sinks clogged fully with dust. So, it is not a bad idea to open it once in a while and clean them. Okay. Here we have a lot of particulate dust. In US also, I think there is a lot of carpet dust over there, and you will actually see that if you have a laptop or desktop, when you buy it new versus you run it for a few months, 6 months, 1 year, it becomes much more noisy. Why? Because the fan is having to do that much more power. First of all, to rotate itself, because it is the blades itself is now covered with dust. Secondly, to push the air through these heat sink, the fin passages, which are now clogged by dust, and many a times hardly any I have seen, I once opened my laptop, the heat sink was just a block. I mean, there's no way any air can flow through it. So what I had to do is I took a vacuum cleaner and sucked all the dust in, and then when I switched it on, man, it was so much more silent. Okay.
Just a quick story.
Yeah.
Dell actually did a study of what this dust is on laptops, not on desktops or servers. And we were part of the study, that's how I know about it. And they wanted to see what the source of all this dust is. And guess what the primary source was? What the single biggest common component of dust in all the laptops? Dead human skin. Very gross, but it was dead skin.
The skins, yeah.
So that clogs up over time, clogs up the
Wow.
all the heat pads.
Wow. So there you go. All right. So these are traditional. These are, I won't say anymore emerging. These are like liquid cooled stuff, and I'll come to liquid cooling. Okay. Liquid cooling, you will hear the term. It has its own merits, definitely. It's important, but what I would say is there is nothing called liquid cooling. Everything has to be air cooled, and I will tell you why. Okay. Liquid cooling, heat pipes are just means to transport heat from an inconvenient location to a convenient location where it can be air cooled. And the whole reason is the fact that when you are air cooling, you bring in cold air, what comes out is hot air, and you just get rid of it and dump it to the ambient. With liquid, you cannot do that. You have to cool that air, cool that liquid back and bring it back in a closed loop, and to cool it back you need an air cooled heat sink. So therefore, finally the heat is dissipated by air cooling, except that it is not dissipated at the place where it is generated, and I will come to that. Notebook, you have heat pipes, and I am carrying a sample. This is what I have worked on at Intel. It's been last 5 years at Intel. I was part of the mobile group. This is a typical heat pipe heat sink solution in a laptop. Okay, and I will pass it on. Give me a minute. Let me show you. All right, I'll pass it on, and later on I'll tell you what a heat pipe is and what it works. So just to tell you that this is where just 1 minute. Yeah, can you please? Yeah. So as you can see, these two what looks as copper rods are actually heat pipes. This is where the CPU is. This is where it's this copper plate to which the heat pipe is bonded actually sits on the CPU, maybe like this. Okay. And then at one end, these heat pipes then come at one end where it is connected to a heat sink like this, through which you have a fan that blows air through. Okay. As this fan rotates, air comes out. You look at your laptop, any laptop, you will be able to see from the exhaust vent from where hot air comes out. If you look through, you will be able to see these fins, this fin array. Okay. And upstream of that is a fan typically. Okay. Why do I need this arrangement? I will come to that, but I will just let you let this get passed on.
So it's not a closed loop?
It is a closed loop, but the air is, I will show you why, how this is a closed loop. Okay. Okay. As we look into it, now let us look a little bit into fundamentals of what is a heat sink. A heat sink, typically we call it a finned heat sink. It will have fins. Now what are fins? If you take a flat plate, flat surface like this, and I have some heat coming out, QA, HA delta T, we know that. That is not enough. What can you do? Can I increase my delta T? Well, coming to Arun's point, ambient most of the times I don't have control. I am stuck to where it is primarily dictated where I am operating, both the outside ambient as well as the local ambient inside your system. TB, well, that is what I am trying to restrict, right? There is a threshold beyond which I cannot go. So that H, well, I try my best, I will do that, I will try my best, but beyond a certain point, if it is just air, how much more can I go? So H is definitely one point, but what about this one, A? Right, let me go to full screen mode. So I can increase my overall heat transfer by increasing the surface area. Now what can I do? If I have space, I can attach a few surfaces like this, appendages that is sticking out of these of this flat plate, which was originally being used to cool. So that is what is called a fin. What am I doing? Let us say I have put 3 of these surfaces. I have made available additional surface area. So, the heat which was directly now getting dissipated from this surface is now going to get conducted through these fins, and while getting conducted it is also going to get lost by convection to the surroundings. So, therefore, the surface area for convection increases from just A of the base to A of the base plus the area of the fins. Clear? So, therefore, originally, and now with heat sink, my Q was H area of the base T base minus T ambient, and in the modified version I will have Q heat sink is H area of the base plus n times area of the fin. If the fin area is, if the area of one fin is 1, then n number of fins times T b minus T a. Okay. Ideally, this is what I can do. Now, I said ideally, why? Practically, this is ideal if the entire fin is at the same temperature as that of the base. Practically, that is not possible, because as the heat is moving from one end to other, it is also getting, first of all, there is a thermal resistance of these material itself. Therefore, there has to be a temperature drop, just like there is a voltage drop if current is flowing through a certain resistance. This resistance may be very small, it may be copper or aluminum, but some finite resistance. The other thing is, it is also getting lost by convection from these surfaces. So, therefore, as I move from the base to the tip of the fin, the temperature is going to reduce, and that is why I have tried to represent this by this shaded picture. So, it is dark red over here, and now as you go out and out, the temperature actually goes down. So, therefore, if I take a small elemental area at this tip, the temperature gradient available is not T b minus T a, but something lower. Okay. So, now what happens is, there is something, and I am not going to get into the details, there are ways to calculate, but there is something called eta fin, which is called fin efficiency. What it says is actual heat transfer through a fin over heat transfer if fin, entire fin rather, is at T b. Oops, sorry. Clear? So, therefore, in reality QHS I can write, and then this is a function of the fin material, the geometry, the heat transfer coefficient around, the conductivity of the material. And so, this is a complete, this is a, let me write it, that function of geometry, H, material, yeah, pretty much these, okay, and geometry is length also. So, therefore, actual QS, so this is real, can be written as H times area of the base plus eta fin n area of the fin times T b minus T a. Okay. So, this is for an array of fins, this is the total heat transfer. Definitely earlier it was H a b delta T, now this is what is added, this is the additional term that I have added. And typically if I choose, and which is what it typically is, if I take copper or aluminum fins and with a fair amount of cross sectional area, the fin efficiency is more or less around 90% or higher. Okay. So, what we lose out in terms of efficiency, which is always less than 1, but we try to go as close as 1 to as possible by taking good conductors of heat. So, most heat sinks are made of aluminum or copper, the one I am passing around you can see is copper. Okay. There may be some contact resistance at these bases as well, we should not, because It is not always extruded from the same piece of material or machined out. Machined out is actually very inefficient and expensive method, wasteful method I would say. But even if it is extruded, many a times you especially the one that I have passed around, you cannot extrude those because these are extremely thin and tall fins. So, there are other ways by which this contact is not perfect. So, you need to add a contact resistance, and as a result the fin will be at a lower temperature compared to the base. But all this taken a little bit here and there, but overall fins help in improving the heat transfer by making available extended surface area. Okay. Number of fins also important.
Yeah, so if the number of fins are more, it will be better, right?
Not always. I'll come to that.
So
Yes.
the thickness also matters, right? Area of the fin.
No, that is correct, but you know the problem over here is, and this is we are going into the second level of details, is if you look at this one, what I have written, the expression that I have written over here, I have taken this h to be the same over here and here. Actually the h is also a function of spacing between the fins, the channel width. Remember I said Nusselt number is a function of Reynolds number, and both in Nusselt number and Reynolds number there was a length scale which typically is what is called, basically it is an effective diameter of a channel through which the flow is going. And if you bring the fins too close to each other, what happens? There will be more obstruction to airflow. So, the less air will be able to go to flow through that, and if I go into the people with heat transfer background and fluid mechanics background will know that the boundary layers start overlapping and so on. But what essentially what it means is when you bring them too close to each other, the effect heat transfer coefficient goes down. Okay. So, it is not, and think of the ultimate case when it is just a solid block, nothing is going to move, everything is going to bypass. So, this expression is not very accurate. This h definitely is going to be altered as you add more and more fins. Okay. So, this is how airflow is happening. This is what is called a plate fin, longitudinal fin, parallel plate fin, heat sink, different nomenclature is being used, but this is essentially how it looks like. There is an array of plates forming channels versus flow through what is called a pin fin heat sink. Here these are like posts or pillars or pins. This can be square cross section, rectangular cross section, spherical, circular cross section, ellipsoidal cross section, elliptical cross section, sorry. And as it goes, what happens is this can be shown that as air flows through, many a times what happens is as you introduce more and more disturbances, the heat transfer coefficient can actually go up, but at the cost of higher flow resistance. Okay. So, just a side note over there. If you look at heat sinks can be of two types. One is called a passive heat sink, where the heat sink just comes like that. Do I have an example? Do I have a sample over here? Yeah. This is not exactly a very classical heat sink. This is from a healthcare product, one of the ultrasound products from GE. This is a sample that again they allowed me to take. So, you can see this is a flat plate and you have very short stout fins sticking out of there. Okay. So, these actually help, all right, but the way it has come is this is just like a heat sink and nothing more. Of course, it is a contoured plate and so on, it is not just a simple rectangular base plate like these. Okay. So, this is what we will call a passive heat sink, whereas, so it can just be a standalone or it can be put inside the system with a fan in conjunction with a fan like the one I am passing around. The heat sink itself is passive, but then I can put a fan upstream of that to flow air through it, all right. So, these are some pictures of that, you have one at your hand. The other one is active, where it comes with a fan, integrated with a fan, and these are some examples. And this is primarily in your computers, if you desktop, if you open it, rip it open, this is what you will see. The heat sinks will primarily look like these. Okay, this picture is interesting, you see how they have tried, your height was limited. So, I could not make the fins very tall, but I wanted higher surface area. So, see what they did, they bent it so that your overall the Z height is reduced, but you have higher surface area. Yeah. All right. Okay. So, this is how some of these are called active heat sinks. Now, how do I characterize a heat sink? And let us take a very simple example of the one that I am passing around. Force convection, I have plate fin heat sink, parallel plate, though generically you can use it for anything, for any other type of heat sink as well, for a pin fin heat sink as well, for example, and I have air flow going through this. Clear? So, how am I going to characterize these? So, the first thing is, coming to your point, is can I indefinitely keep on increasing the number of fins, and which essentially means I will indefinitely keep reducing the fin spacing. Yes, surface area will go up, but your H will go down. Okay.
How important is surface finish in the fins?
It is at the next level of details it is. So, people have looked at sandblasted surfaces, dimpled surfaces. So, if you are trying to eke out the next 2%, 3%, 5%, yes, it is important.
So, where I am going with that is, if you dimple it, you have effectively increased your surface area, but have you also heard the boundary layer created more friction, drag?
Yes. From the heat transfer point of view, I have helped it, but I may be able to reduce. From the fluid point of view, I have hurt myself. So, I will come to that. Now, let us say I take a heat sink like the one I am passing there, and then I have a here it is. So, this is my heat sink, and then this is a fan, and I switch on the fan. How much is the flow rate that I am going to get through the heat sink? That is the question. What is the flow rate, what is the velocity, and therefore, the velocity through each of these channels that I am going to get? Very important question. So, the way that is done is, now what is it that it is going to dictate how much flow I am going to get? That is known as the flow resistance, measured typically by the pressure drop. Okay. So, if I take a heat sink and I am drawing the side view, this is my base and this is my longitudinal fin, and I pass air through this at a certain velocity v. What will happen is, if I measure the pressure over here P inlet and I pressure over P outlet, and this is my delta P, this delta P is a measure of flow resistance. Okay. So, higher is my flow resistance, higher will be the pressure drop, which means if this is the exit, for example, and which is typically going to be ambient, then my fan has to build up a higher pressure for the same velocity to flow through this. Clear? All right. So, if I take a channel heat sink like a parallel plate heat sink like this, or even a pin fin, etc., I can do a bunch of tests in a wind tunnel and find out what is, and get a curve for my delta P times flow rate. So, I would say it is called a system resistance curve or a resistance curve, sorry, resistance curve is essentially delta P versus Q, where Q is the flow rate. It can be sometimes expressed in CFM, cubic feet per minute, sometimes meters cube per second, and so on. Delta P typically is Newton per meter squared or pascals, or sometimes even inches of water. Okay. So, by doing a certain, if I take a heat sink, I can plot a delta P versus Q curve, which typically a system resistance curve. Well, when there is no velocity, there is no pressure drop, there is no flow. So, why is this pressure is going to be equal to this pressure. So, it definitely starts from 0, and then this is typically how it looks like. Clear? So, this is my system resistance curve. Now, let us say I increase my number of fins. What happens? The system resistance is going to go up, because my channels are now becoming smaller. It is the flow has to squeeze through narrow channels right now. So, as my number of fins increases, my system resistance curve moves upwards. So, which means for a given Q, my delta P is higher. Okay. So, this is what I am showing over on this slide. So, let us take, if I take any heat sink, or for that matter any system, this is the system resistance or system impedance curve given by blue. Clear? Now, When you buy a fan like this, a manufacturer will give you what is called a fan characteristic curve, which is also a pressure drop versus flow rate curve. Okay. So, which means if your system pressure drop is very high, then what happens is I will be able to handle that kind of pressure drop, but mind you, your flow rate is going to be very low. Okay, like your battery or an EMF source, if your resistance is high, your current is going to be low. If your resistance is low, current is going to be high, same thing. But over here, the way it's not a very simple equation like V equals to IR. What we have, however, here is you have a fan characteristic curve, you have a system resistance curve, and where they intersect is going to be your operating point. Okay. So, therefore, when I am designing a system, I have a system resistance curve for this heat sink, I have a fan characteristic curve for this fan. When I put the two of them together, the flow rate at which this combination or this system of fan plus heat sink is going to operate is going to be determined by this intersection point, which is known as the operating point. Clear? So, therefore, now let us come back here and let us say this was my fan curve given by the fan. Okay, this is fan curve. So, what it means? It means that if I have fins that are spaced farther apart, I am going to operate at a higher Q, and if I have fins which are very close to each other, dense fins, more number of fins, I will operate at a lower flow rate. Okay. So, this is very important. To get at what flow rate I am going to operate my system on is very important. So, I am showing you just the heat sink and fan curve here, heat sink and fan as an example, but actually when you put it in a system, the flow resistance for every other component inside the system also gets inducted into this system impedance. This is not just the resistance it has to overcome for flowing through these channels of the heat sinks, but everywhere else. Okay. So, now I know the operating point, but what is important, I want to design my heat sink. I know what is the flow, and then depending on the flow I will have a theta versus flow rate curve. And so, I will have a theta versus flow rate, which is going to be a function of CFM or the flow rate, cubic feet per minute. So, first what I will do is I will come here, find out the operating point, plug it in this direct equation, get the sink to ambient thermal resistance, and from there I can calculate the sink resistance and therefore the junction resistance and so on and so forth. So, this is how we characterize a heat sink, or rather design a heat sink for a certain system whose temperatures and other conditions are given to us. Okay. So, having just a concluding note is having too many fins may help or hurt you. I mean, this by itself is not a disadvantage. It's so what? Okay, I am operating at a low flow rate, but even at this lower flow rate, the heat transfer coefficient and therefore the thermal resistance that I can give you is going to be lower than what I will give for this heat sink at a higher flow rate. Fine, I will go for this. Okay. But many a times, especially in academic papers, a mistake that we see over here is when they are trying to come up with new heat sink designs, they are always doing a comparison at the same flow rate, and which is not correct. Okay. You have to do a comparison based on a fan curve and show that even at a lower operating point my heat sink performance is better than your heat sink at a higher flow rate or higher at a flow rate corresponding or an operating point corresponding to a higher flow rate. Only then is my design better than you, not just at a given flow rate, because I may not be able to attain that flow rate in the first place. Clear? Okay, sorry, let us take a break here. I hope the tea is ready by now, and we will come back and finish this part. Okay. Thank you. On our discussion on thermal technologies, cooling technologies. So, just before the break we talked about how do you characterize a heat sink, and we saw that of course thermal resistance is the single most important parameter, because that is what we want to minimize in order to keep the temperatures cool or increase the amount of heat that we can dissipate. But it is also important to know that at what flow rate am I going to take that thermal resistance, and which will be which will depend on what is the geometry of the heat sink that you are using and what is the fan that you are using. Okay. Okay. So, these were primarily air cooled heat sinks, which is what is used. There is also something called liquid cooled cold plates, where what happens is, instead of putting a heat sink and a fan on top of the CPU, you put a plate which from outside will look like just a plate, like a copper plate, a thick one, but inside what you will find is typically either a straight flow or a serpentile channel like this. It can be parallel channels as well with an inlet and outlet plenum, or it can be one inlet, then a serpentile movement in serpentile path inside, and then the liquid comes out from an outlet. Okay. So, essentially what happens is a cold liquid comes in, a hot liquid goes out, because the heat dissipated by the CPU is picked up by this liquid. Okay. In an extreme case, not extreme case, in certain cases you may also have scenarios that when a liquid comes in, but what exits is actually liquid plus vapor. So, you start having phase change or boiling heat transfer inside. We call that flow boiling, as people with heat transfer background will know. And there what happens is, the way that we can achieve flow boiling, as you know, in flow boiling the heat transfer coefficients are much higher compared to single phase, but so is pressure drop. Pressure drop is also much higher compared to single phase, right. So, we have to again do a trade off and see whether it is worth going through to two phase heat transfer at a lower flow rate versus single phase heat transfer at a higher flow rate, and see where the heat transfer coefficients and effective thermal resistances, how do they match, how do they compare. Okay. But it so happens it is possible to have two phase flow as well and flow boiling inside. So, in which case what comes out is a liquid plus vapor mixture. Typically it is never superheated vapor. Okay. Now, this is an example of so this was just showing the cold plate, but how will it look like in a system? Very important. Okay. Again, you will find a lot of papers in academia, including some from me on microchannels, where I just focused on this one and not on the system, and I will show later that one of the works, it was good as far as giving new insights to flow boiling inside a microchannel is concerned, but when it came to a system context, it was not at all worth the investment, and I will show an example in the afternoon. But let us look into this now, more into the fundamentals. You have this cold plate, and this is what we are talking about. A cold liquid comes out, coolant comes in and exits it at a higher temperature. Then what happens? In the heat sink you just dump the air outside, the hot air outside, but in the liquid we cannot do that. So, what do I have to do? I have to bring this back and take it to somewhere where again I will have a heat sink and a fan. So, this hot liquid will now therefore cool down because of this, by this cooling air, and then it comes back to the cold plate. Now, again it just cannot flow by itself. Sometimes it can do natural circulation loops due to just gravity differences, it can, but for all practical purposes we will need a pump. That is what is going to make this coolant flow through this closed loop. Okay. And this is an example of a cold plate. This is the cold plate that sits on the CPU. One of them is the inlet, the other is the exit, and then it comes to a heat exchanger over here, which you cannot see. There is a pump, and then there is a fan blowing air through that heat exchanger. Okay. The reason I put this picture is look at the relative sizes. Why am I going for this? Therefore, because finally look at this bottom line, I am saying finally everything is air cooled, because the heat that I picked up over here, or the liquid picked up over here, is being rejected over here. Finally, it is the air that is cooling, that is dissipating that heat. Therefore, why not put this heat sink and fan over here itself? And this is where this picture comes into the it drives the message, in the sense that in order to dissipate that heat, you need a heat exchanger and a fan assembly of this size. You cannot put it over here. Okay. So, therefore, I will put it in a position where I have the real estate and the space, which is not necessarily at the location where the CPU is present. So, therefore, what this liquid is doing, or this coolant is doing, is essentially transporting the heat from this location, which was not a convenient location to put the final thermal solution. Okay. So, it is transporting the heat from an inconvenient location to a convenient location. That is it. So, finally, again I want to end the slide with this keyword, finally everything is air cooled. Yeah.
So the hardware that you were passing around
Yeah.
from a laptop, that's also liquid cooled.
Same thing.
So where's the pump?
Okay, coming to that. All right. Next question. The hardware that I move past around here, it's a heat pipe. Okay. So what is a heat pipe? So let me give you a history. Heat pipe was first used by NASA in their space launch missions. The original heat pipe was several meters long and probably almost 6 to 8 inches in diameter. Essentially, at this point, not getting into the details, it is an excellent conductor of heat in the axial direction. Remember, I said CPU the copper has a thermal conductivity of 400 watts per meter Kelvin. A heat pipe can have several thousands in the axial direction. Now, how is it possible? Is it a pipe with a certain solid material? It is not, and we will talk about that. Why was it used in NASA? Is because in the spaceships itself, depending on which side it was facing, there was a lot of temperature gradient from one end of the spaceship to the other. So, this was used to equilibrate the temperatures to a certain degree. Okay. Extremely expensive. From there, we use it today in a laptop. It comes for less than $1, I think few 20 cents or 30 cents today. Extremely reliable. I mean, as I was telling you, I worked on thermal solutions of mobile computers for 5 years. I never saw a single heat pipe fail. Okay. Many times we actually cut them open to see what is inside, which was intentional destruction, but otherwise heat pipe never fails. It has reached that level of reliability and it is high volume manufacturable. Several companies around the world doing it at and every laptop today almost has it. How does it work is the question. So, I have an animation over here which will tell you. This is how this hardware that I passed around looks like. This was a special one where it has one of the heat pipes came on the fan casing, but forget that, that is not a standard one. It typically it will have either 1 or 2 heat pipes getting into this finned heat sink and a fan blowing air through it. Okay. So, why is it done here? Because this fan and heat sink is too big to be put inside on the motherboard in the laptop. Laptop, as you have seen, it has certain thickness, and again you have motherboard cutting through around half, maybe not exactly half, it is not always symmetrically. But again, the real estate that you see, the what we call the internal Z height of a laptop, the entire one is not going to be available on the top of the CPU to put this heat sink. So, therefore, we take it on the side at one end near the exhaust vent and put this fan and heat sink. So, this is where the heat is rejected, this is where the heat is extracted from the CPU, and they are not at the same location. So, therefore, the heat pipe is given as a means of transport, again what I was talking about, inconvenient to a convenient location. Now, how does it work? It looks like a solid rod, right? Actually, it is not. It is actually a hollow rod. It is a hollow copper pipe you can think about with a few drops of a liquid, most commonly water, and at a lower pressure, typically 0.3 atmospheres or so on. Why low pressure? Because boiling point of water at 0.3 atmospheres is around 70 degrees centigrade. Now, what happens? If one end of a heat pipe is heated and the other end is cooled, then what happens is that liquid on the hot end evaporates and it becomes water vapor. The water vapor then flows through the central core, okay, and goes to the other end where it is cooled by in this case by this fan and heat sink, and thereby it condenses. Okay. So, the liquid condenses. Now, how will the liquid be brought back? That is the question, right? How do you pump it back now? The way it is pumped back is by a material or a layer called a wick. So, this pipe, if I take this circular pipe over here, as you can see, the annulus has a material which we call the wick. The wick can be a fiber, it can be sintered metal, various things. Okay. What it does is, because of the capillary action, the water, the condensed water drops flow back through the wick to the evaporator section, and thus what you have is exactly almost all the steps of a liquid pumped loop. You have water flowing over a heated surface where it changes phase. The vapor flows to a cold end where it is cooled and condensed, and the condensed liquid comes back due to capillary pumping action in the wick. Okay. Why does it come back? Capillary action, you have all lighted a diya, right? Through the wick, the oil comes from the diya to the tip where you light the fire. Same thing here. Okay. Yes.
So is that wicking efficiency, does that drop off with length? And if
Of
so,
course.
how rapid?
Absolutely. Absolutely. So the thumb rule, that's a very good question. We can do a lot of analysis, which I am not going to do here, but it can be shown that this, of course, this pumping action, so the pressure rise, the pressure head that the pumping action, the capillary action gives, what is it balancing? It is balancing the flow resistance due to flow of the liquid through this porous medium. Okay. And people who are familiar with porous medium, there is something called a Darcy law, mu u over k. It is overcoming the frictional pressure drop because of the flow of the vapor through the annular core. Okay. Darcy-Weisbach formula, friction factor. Okay. I mean, even if you do not know it, not a big deal. And then depending on if the heat pipe is, where the evaporator is, how it is oriented, if the condenser is at the top or the evaporator is at the top, depending on that, the gravity may assist the flow of the condensate back to the heated section, or it may oppose. So the pumping action of this wick or the capillary pressure, the pressure rise due to capillary action, must overcome these three sources of pressure drop. Okay. The pressure drop due to vapor flow, pressure drop due to liquid flow, and gravity if it is depending on the orientation. All right. So now if you do this momentum balance and work out of all the things and come up with what is going to be the flow rate, etc., it can be shown a thumb rule, and it is also followed quite regularly. If I consider a straight heat pipe, the heat carrying capacity, the maximum heat that you can transport, is inversely proportional to the length through which it has to travel. Okay. Because each of these pressure drops is a function of length, right? And if you have bends and all like these, they all add up. Okay. These heat pipes that you just saw, these are actually round heat pipes which are flattened, very common in laptops. These are typically 6 millimeters or 8 millimeters, then flattened to 2 mm by, I think this was a 4 mm, flattened to 2 by 6 or something like that. Okay. All right. So this is a very important point, and I am going to show one example where somebody is doing something to overcome this length restriction. Okay. If it has to transfer the heat over long lengths, then of course your diameter has to go up, the amount of liquid that you put in has to go up, and so on and so forth. Okay. All right. So any questions how a heat pipe works? Okay. Very fascinating technology, of course now very mature and almost there everywhere. I think Apple computers are like 1 mm thickness heat. Okay.
And you said that they're not at ambient pressure inside.
No, they are at,
sealed.
this is sealed, absolutely.
And you say there are no failures of that.
No, no failures. You can see how it is,
Right.
how it is evacuated and then crimped at the end. No failures.
So what is the material of the wick?
That depends on the, sometimes it is sintered copper, sometimes it is fibrous materials as well. It depends on the, many of the manufacturers keep it a trade secret. I can send you some of the things that I do not have it in the slide, but I can send you some examples. Okay. By the way, other thing is many a times when you go to very small dimensions, which are also called micro heat pipes, then many a times it is not a wick anymore, because just the nooks and corners themselves provide, and sometimes it is small channels and grooves cut along the internal wall, they themselves provide the capillary action. Okay. So, and there are also variations now going thinner, where instead of the wick being at the annulus and the core being at the center, it is reversed. The wick is along the center and the vapor actually flows through the annulus. So, all kinds of variables are possible, but this is the most common one. Yes, please.
So can we use heat pipes where hot junction temperature is as low as 5 degrees, 10 degrees?
What is the cold junction temperature? It is a conductor finally.
Yes, but then
Oh yeah, right. 5, well, you cannot use water then, you have to use some other liquid, other liquid. That is also there. Okay, so let's go back now here to the main slide which you have with you.
So just as out of curiosity,
Yeah.
is there some special coolant chemical in here, or is this water based, the one that you?
Water based, they are all water based. Water is because it is benign, because other chemicals you may have environmental issues, it may have whatever leakage, if it leaks it may have electrical issues as well. So water, that even if it fails, and the other good thing is the amount of water inside is first of all very small, and what happens is I once, as I said, I cut open a heat pipe, it is already, and just to see how much water is inside, and it almost flashed, okay. Because the moment it just evaporated and it just because of the sudden change in pressure, but I could just see a little feel a little dampness on my fingers, and I asked him, where did the water go? I don't know. Okay. So what is the final effect? I mean, there is a lot of very good physics inside what is happening, but effectively what was my goal? My goal was to conduct the heat from the site of extraction to the site of rejection. How good is it that how good is the heat pipe in accomplishing that function? Effective axial thermal conductivity can be 10,000, copper is 400. Okay. Now when we come to very thin heat pipes, it is probably a couple of thousands, but still way higher than copper. Okay. Very light, very reliable, very cheap today. It was not so in the 1950s or 60s when NASA came up with it, but today nobody even questions. And you say, I want to put a heat pipe, yeah, go ahead, 20 cents. If it can help me, no problem, go ahead. Okay. Now there are also 2-dimensional heat pipes which are also called vapor chambers. So instead of being a round tubular form, it will look like a sheet of metal, okay, but actually inside it is a hollow sheet with a wick around the periphery, and then vapor and then hollow inside. So if you have a heat source like this, and you have multiple heat sources, then what happens is the water vaporizes, goes over here where you put a heat sink, or the heat is lost, it condenses and again comes back by the wicking action. Okay. So these are called vapor chambers, 2D heat pipes, extensively being researched and also used in some of the tablets and cell phones. And I will try to show today an example where somebody whom Professor Dasgupta knows very well, who was also one of my former teachers in US, he has come up with a vapor chamber based, we call it heat spreader, because that is what it is doing, and which is like a few less than a millimeter, less than 0.5 millimeters also, and I do not know how he has done it. I mean, I know how he has done it, it is fascinating how he has done it, and it is being used or being targeted for the cell phone and laptop market, cell phone and tablet markets. Not there yet, but definitely way better than whatever is used and available today. Yeah. Okay. Finally, refrigeration cooling techniques. So this was pump loop that we talked about. What is the minimum temperature? So if I take a pump loop like this or a heat pipe, whatever, what is the minimum temperature I can cool this? That is the ambient, because that is the lowest temperature in my system. In fact, I can never cool it to ambient, but that is the minimum that we can do. What if you want to go even lesser? It is not possible. Second law of thermodynamics tells you it is not possible. Heat cannot flow spontaneously from a lower temperature to a higher temperature, but it can do so, second law tells you, only if you apply or if work is done on the system. So that is how, and what is that? Typically what we know of such a system is refrigeration. Refrigeration, I can remove heat from a lower temperature to a higher temperature. So of course the temperature inside our refrigerator is much lower compared to the outside ambient, but I am rejecting heat from the refrigerator to the ambient, and the way I am doing it is by using a compressor, because I am now doing external, I am actually supplying energy, right. So typically I have this in a refrigeration system, I have an evaporator, I have a condenser, I have a compressor, and I have an expansion valve. I think people with thermal background knows this very well, even if people who do not have a thermal background, I think this itself is good enough. Okay. I have a refrigerant, of course I cannot use, I can use water, but typically we do not. In a refrigeration system we typically use a refrigerant 134A, R12 and all that stuff. Now again the inorganic refrigerants are coming back, CO2, ammonia, but anyway. So, the refrigerant, what happens is it flows through an evaporator which is kept in the position you want to keep cool, and when the refrigerant comes here it is at a very low pressure and temperature, okay, and typically at the entry it is at the two phase state with more liquid and less vapor. As it flows through the evaporator it converts from liquid to complete vapor, and then as it comes out it is in the vapor state or gaseous state. Then we use a compressor to compress it to a higher pressure and temperature, and then pass it through a heat exchanger where it rejects heat to the outside and condenses, and then passes through an expansion valve where it is there is a sudden drop in pressure and it comes back again to this low pressure and temperature. Okay. This is how a refrigeration system works, but essentially if I use this refrigeration system as a black box, I can keep the refrigerator the evaporator on the surface that I want to cool, in this case my chip, and reject the heat to the ambient by keeping the condenser at the ambient. Think of your split AC, what you have inside the room, that nice white thing that you see, that is the evaporator, and what you have outside is actually the expansion valve, condenser and compressor, primarily the condenser, and that is where the heat is rejected to the ambient. So, the heat is actually flowing from the room which is probably you have set it at 20, 25, 20 degrees centigrade, and on a typical Kharagpur summer day where the outside temperature can be as high as 45, even 47 I think. So, you are actually extracting heat from a room which is at 25 degrees centigrade and rejecting it to an ambient which is at 45 degrees centigrade. Okay. Spontaneously not possible, but it is possible because I am doing external work, mechanical work through this compressor. So, refrigeration has also been used, and I am going to show an example later, but again that does not come for free. Of course, nothing comes for free, all these components cost money, but it does not come for free even in terms of energy, because what you reject finally is actually more than what you have extracted, because Q out in an ideal system with no loss will be Q in plus the work compressor inlet, first law of thermodynamics, right. Okay.
But what would be the typical size of the system?
Wait till second half, I will show you. That is the challenge, especially see heat exchanger, expansion valve, etc. you can miniaturize, compressor, that is the challenge. Okay, I will show you. Actually Intel developed along with a company in Brazil called Embraco, and I will show that is in public domain. Okay. The other thing is called again continuing on refrigeration, is called thermoelectric refrigeration. Okay. Now, what is thermoelectric refrigeration? So, thermoelectrics, if you just to give you a background, it depends on this, it basically is hinged on Seebeck and Peltier effect, if you remember. Seebeck effect says that if you have a temperature difference, if you have two materials, dissimilar materials connected at two ends, and you have a temperature difference, you are going to give rise to an EMF, okay, and therefore you can measure a voltage across, and there will be a current flow and you can measure a voltage across it. That is Seebeck effect, and that is the principle of operation of any thermocouple. A thermocouple typically are two wires of two dissimilar materials joined at one end, which is the hot junction, can be the cold junction also, which we put on the surface whose temperature we want to measure. The other end is put at some standard temperature, and measuring the voltage across, we can correlate that voltage to a temperature. Peltier effect is, it is not exactly the way the Peltier cast it is not exactly the same, but loosely what it means is the opposite. If you have such a system of two dissimilar materials and you actually force a current to flow through by applying an external EMF, then you are going to give rise to a temperature difference across the two ends. Okay. All right. So, if that is the case, can we try using that? Now, if you take materials, regular metals, chromel, aluminum, like we use in thermocouples, etc., then the amount of voltage etc. that you can get or can be very, very small. Okay. I mean the delta V over delta T, that Seebeck coefficient, is not going to be very high. Okay. But it turns out that if you go to semiconductors and then look at p doped and n doped, and bismuth telluride is one of the most ideal materials. So, if you take a p type and n type and then connect them such that they are electrically in series like this, you see they are connected at this end, and I am just showing one such couple and I am applying a voltage across it, then what happens? The current is going to flow in this manner, right. As the current flows, due to thermoelectric effect, I am going to give rise to a temperature difference. In this case, if this is the direction, then this will be my cold junction and this will be my hot junction. I will be able to remove heat from this end and reject it at the other end. Okay. How is this possible? It is possible, or how can I draw a parallel with a regular refrigeration system? Yes, the heat is flowing definitely, but where is the work? I have had a compressor here. What is doing the work here? That is a thermoelectric effect. The work that I am, the energy that I am applying externally is electrical energy compared to mechanical energy in a compressor. Of course, the compressor also needs electricity to run, but finally the work input is mechanical work, right, whether it is a reciprocating compressor or it is a centrifugal compressor, whereas here the input energy is electrical energy. Okay. So, this is how this is actually now very commonly available, pretty cheap. This is one such Peltier couple is what its talk is. You have a series of many of these pairs of p and n junctions arranged inside here. Okay. You can buy them of that, you can, if you go to Amazon you can buy these. Okay. What is the advantage? It is very light, very compact, very cheap also, no moving parts like a compressor, noisy, moving, you have to lubricate, all that stuff. Can reduce temperature below ambient, obviously that is what we are using it for, but extremely inefficient. The amount of heat that you can remove versus the amount of work that you have to put in, that ratio is very, very low. Okay. Typically, when it comes to refrigerator, instead of efficiency, we use the term COP, coefficient of performance, which is the ratio of the amount of heat that is extracted over the amount of work that you put in. In a typical refrigerator in your household, that COP is around 3.54 today, the basic ones. Of course, there are more advanced, more expensive ones. COP of a thermoelectric, low single digits, 0.3, 0.2. Okay. But again, very small, very compact, can put it at certain locations. You do not have to think about bulky parts like in a regular refrigeration system. So, that way very handy, but inefficient, right. So, it is useful if you want to reduce the temperature at a certain location, but finally what you are rejecting is much more than the heat that you are absorbing, right, because what you are rejecting is the heat that is absorbed plus the electrical energy that you have supplied, which is several times higher than what you have removed. So, therefore, thermoelectrics can be used if you have if you need a localized cooling somewhere, but you have headroom for overall system level cooling. Okay. And what do I mean by that? Probably will be a little more clear when I talk about system level design. Okay. So, summary, I think this is okay, this is all self explanatory, you have this slide. Okay. Yes, please.
Very dumb question. Can
Yes.
you go back to the thermoelectric?
Yeah.
Thing? So, the heat is not being removed as heat here, it's being converted to electrical energy and then being removed?
No, no,
No,
it's heat.
It is being,
Yes.
So, how the phonons traveling from cold plate to the hot plate?
Through conduction, this N and P junctions will have their own conductivities and L. So, just L over K. I will actually come to that, what are the properties that actually govern,
Right.
and why this was such a challenge, or this still is such a challenge. I will come to that. Okay. Modeling techniques. Why do we need models? We all know building prototypes is expensive. So, you cannot try out, if you have like 10 options, you cannot build 10 systems and try them. Okay. You have to down select. Finally, definitely you are going to test it before releasing a product, but the initial shortlisting, down selecting it to the top 3-4 candidates or 2-3 candidates, we need modeling. Plus, it is not possible to measure everything. So, when you are doing an experiment, you can measure probably some temperature, some pressure, some I am talking about again thermal modeling. So, certain temperature, certain pressure, certain flow rates. But for example, in the laptop I can measure how much is the total flow that is coming out of the system, out of which how much is going near the CPU, how much is going near the memory, etc. I do not know. I can use my engineering judgment looking at the layout to say, okay, there will be more flow here, less flow here, but actually how much, models will help me. Okay. So, it allows for quick what if assessments. What if I did this? What if I put a vent over here? Is it going to help solve my problem? Okay, try out in the model, see if it works, then only I am going to put it, because otherwise, for example, in the laptop skin, if I have to put a vent, it calls for a complete tooling change. It is very expensive. Okay. So, I have to get it right the first time. Okay. But caution, models cannot replace experimentation. Let me be very clear about that. I will tell you a story. When I first joined Intel in USA after my PhD, and at that time microchannels was a hot topic, and this was one of the first projects given to me. I try out, see whether it will work or not. So, I came up with some models trying to model two-phase flow, not easy, but okay. And finally, there were some experiments done from Stanford University, I got good agreement. So, my manager, my teammates were all excited, and then they set up a high level review with some of the directors and VPs. You go and present 10-minute slot. I went and presented my results. Okay. So, this is, in US they do not tell you on your face, but they sugarcoat you and tell you, so, Anand, very good work, yeah, but let me tell you, at the end of the day, we sell products and not models. Okay. Models do not sell. I said, okay, I got the message. So, show that it works, show me experiments, not models, show me data. So, that phrase, models do not sell, has remained with me. I know some of my students also, I bug them with this with this phrase. Many a times they do not like it. It is important to do modeling, it gives us a lot of insight, physical insight, understanding, etc. But finally, you have to show that it works. Yes.
Since there are a lot of students in the back, I want to add another very interesting statement to that stuck in my brain. I heard that from another colleague years ago, and it goes something like this: no one believes a model except the one who did the modeling. Everyone believes in experiment except the one who conducted the experiment. The experimentalist knows what errors and approximations you have to make in all the measurements and in the experimental technique. So he or she knows what the errors in the experiment are. The one who's observing it says, hey, that's hard data, I can see it, therefore I believe it.
Okay. So, that is where the last one, models must be validated. Okay. So, what are thermal modeling tools that we normally use? See, there are two types of models that you can do. One is just a finite element based, where the primary heat transfer mode is conduction. So, that example that we were talking about, the dye, then the TIM, etc., even including spreading and all, I can do a pure conduction mode, because I am not modeling flow. I am only solving, in terms of solving differential equations, I am only solving the energy equation, and that too just with conduction terms, no flow. So, that is sometimes used. If I characterize a heat sink and get a thermal resistance value, I can convert it to 1 over HA, calculate the equivalent H, and in my model use it as a boundary condition. Okay. On the other hand, if I do not know and I want to look at the flow fields, the pressure contours, the temperature contours, etc., I have to do a flow model. And typically, the ones that are largely used in the industry today are Fluent, IcePack, which is a subset of Fluent. It uses the same solver as that of Fluent, but a much more user friendly preprocessor and postprocessor. And Flowtherm. Flowtherm was owned by Flowmerix, and I think it was bought over by this company. I am forgetting the name. The name is skipping my mind now. Okay. All right. So, this captures this flow model. If you want to use any of these, you would need it, or you need to use them if you want to capture the convection and radiation effects in addition to conduction. Okay. And it allows for determination of flow rates, velocity contours, pressure distribution in addition to temperatures. Okay. So, this is a package level modeling example. So, this is yeah.
So, what do you say the Flowtherm is the right tool to use it, or
There is no right or wrong. I mean, these are available tools.
okay.
So
Loaded question.
there's no right or wrong, because there's star CCM plus.
No,
There
no.
is.
I am asking this. I heard about the names thermal tools in Intel. The few people use ANSYS, few people use Abacus, few people use Flowtherm, few people use ANSYS and Flowtherm.
Right. Okay. Correct. So let me tell you. So the ANSYS, Abacus, Patran, what you are talking about, this you can use only if here the boundary condition is a convection coefficient. Okay. So if it's just conduction that you are trying to do, you can use them. If you want to look at flow, etc., then the regular ANSYS that we know about, the finite element, even though now Fluent is also called ANSYS Fluent because ANSYS bought over Fluent, but any of these finite elements, traditional finite element softwares, that you cannot use to model flow or solve flow equations. So therefore you cannot get pressure, velocity, all that information. Now Fluent, IcePack, Flowtherm, these enable you to solve for this. There is also star CCM plus, there is COMSOL. Okay. They can all solve for the momentum and energy equations. All right. So if you want that kind of information, so Patran, Abacus is not going to. So what you are saying, ANSYS and Fluent, that is because ANSYS probably if you just need conduction analysis, Fluent if you need convection and flow analysis as well. Okay. Now Flowtherm, within Intel itself both Flowtherm and IcePack are used depending on the group. Okay. So this is an example of a package level model where no flow modeling, only conduction. So see, I have a motherboard, I have a socket, I have an interposer, solder balls, all this stuff. Now solder balls, am I going to model each of the solder balls? You can, but if I am trying to get primarily an information at the die level temperature, what I will do is I will just model it as a certain layer of certain thickness and assign it an equivalent thermal property, in this case thermal conductivity. Now how will I assign that? Through the solder array. So what is a solder ball? It is either solder balls plus the underfill or solder balls and air. So as the heat flows down, there are two parallel paths. Okay. One is through the solder balls and one is through the intermediate spaces, parallel paths. Okay. So I can, using the law of parallel thermal resistances, I can find out an equivalent thermal resistance and therefore an equivalent thermal conductivity in the downward direction. So that is what we do. In the solder balls, that is what I will, I am not modeling the individual solder balls.
So you take the whole number of solder balls and then do the
correct. Yeah. And I put it, okay, this is the equivalent conductivity which is going to remain, which is going to be somewhere between the solder and the, whether it is underfill or air. Okay. That is what I will do it. Okay. Similarly for thermal interface materials, we typically characterize and then attach a equivalent thermal conductivity to that. Okay. Then heatsink base, and on the heatsink base, instead of modeling the fins, I put an equivalent heat transfer coefficient, very commonly used. So now the analysis is completely conduction based. Okay. 2D conduction, if for all this spreading and all, it will capture, no problem. And this is an example of a temperature contour from the side view. As you can see, the silicon is the hottest, and then as you move up and down, the temperatures go down. You also see this non-uniform temperature distribution because of spreading, right. Many a times on the silicon die itself, we will put as a heat source, we can put a power map, not just 10 watts uniformly spread, but maybe 8 watts over only 10% of the area and 2 watts over the rest 90% of the area, which is your core and cache. Okay. And this is how it will come out to be, and this is the non-uniform temperature distribution. This maximum temperature is what dictates my thermal design. You can say 100 degrees and this is at 40, it does not matter. If this is 100 or more, my design has failed. Okay. And this shows the heat transfer paths. This is how it goes down. Most of it goes down, a little bit comes down. So because I do not remember, but I would have put a pretty high heat transfer, equivalent heat transfer coefficient over here, so that most of the heat was flowing in the top direction. Okay. One more trick. Any modeling will need you have to create a mesh, finite difference finite element, and depending on the mesh count, that is going to that dictates how fast or how slow your model is going to run. Now, I am talking about a heat sink base which is probably 5 millimeters thick. I am talking about a thermal interface material which is 50 microns thick. Okay. If I have to mesh the 50 microns at least with 2 elements, then 25 microns is my mesh size in the vertical direction. It is killing. Okay. I do not want that. So, what a trick that is often used with of course some penalty in terms of accuracy is, finally, it is the thermal resistance L over K A. So, I increase the thermal conductivity of the thermal interface material by a factor of 5, 5 is just a number I am picking. I increase the thermal conductivity by a factor of 5, I increase the thickness by a factor of 5, L over K A remains the same. So, I capture the temperature drop across the fin accurately, across the TIM accurately, but I have also increased the size, I do not have to go to such fine mesh. Okay. Some of the tricks. Okay. I am sure everybody has these tricks up their sleeves. Every company will have some trade secret sleeves tricks as well, but this is something pretty commonly used. Yes.
How difficult is it to deal with interfacial contact resistance, thermal contact resistance?
In terms of modeling using these, it is very difficult, but you can either have to go to this molecular, have to go to the very fine level of thermal modeling.
The reason I am asking is on the solid mechanics side, we use what are called cohesive zone elements to model an interface that is not behaving like a bulb. Is there an equivalent in, and they are commercially available in these codes? So
no,
they
here
have 0 thickness, but you can assign them effective properties.
Right, here also it is there, but it is just a number that you can assign.
Play with that
You have to play with that number. I do not think there are any predictive models that way. So, Mike Jovanovic, for example, he has come up with some contact resistance models. It is pretty much used pretty widely, I would say. It is function of roughnesses, function of pressure, function of the hardness of the materials, and so on and so forth. So, many a times we use those and calculate the effective thermal resistance and put it in the model. Okay. These are some examples of a system level model where I am modeling flow as well. So, this was for example flow through this is a fan put inside a converging duct, and then the fan will have an inlet at the top. Okay. So, the fan sucks in air and then blows it out, and then through this duct, as you can see how the flow kind of converges, and of course, as it converges the velocity has to go up. Okay. This is a heat sink, flow through a heat sink. This is the entry, this is the exit. So, as you can see the temperature is lower at the entry, and as the air heats up, the heat sink temperature also heats up. Okay. So, these kinds of temperature distributions you cannot get over here, because you are assigning an uniform temperature convection boundary condition at the top. Okay. But if you want these distributions, you have to go to flow modeling. Here also you can see flow through a channel with a heat source and a heat sink at the top. This is the velocity contours at a certain cross section. Okay. Model validation very important. Garbage in equal to put in garbage, you get a garbage out. So, it heavily depends on the assumptions that you put in, and you have to be very clear about those. You have to put the right disclaimers as to this is the set of conditions under which my model predicts. And many a times what happens is experimental validation often helps us to fine tune the model for predictive purposes. Okay. So, let me just end this session with a quick example of a system level thermal model. So, let us take a laptop here. Okay. What does a laptop have? It has a CPU and with a heat pipe and heat sink arrangement. This is the heat sink, this is the fan, heat pipes running like this. The heat pipes can, by the way, can end over here. It can have 2 heat sinks also, like the one shown here, does not matter. You have memory, okay. You have VRs, voltage regulators, you have a optical disk drive, which is normally going out of the market now. Very few have CD drives, pretty much not there, except the thicker ones, 15-inch ones may still have. Okay, and various other things. Okay.
So, speaking of that architecture, 2 heat sinks and 1 fan to reject it. If you look at the Microsoft Surface, it has 1 heat sink, but 2 pipes to 2 fans.
2 pipes to 2 fans, yeah, that is also possible.
Reject a lot of heat, or is it what's going on over there?
One, no, so it's using a single heat pipe to what? So it goes to 1 fan first and then to
no, single heat sink, but there are 2 heat pipes coming out of that and going to 2 fans.
Oh, okay. So they're using a shared heat sink, what they call. So what happens?
Too much heat for one pipe? Is that what's happening?
No, not necessarily. Possible, yeah. That is not necessarily, because if what you so it's two different heat pipes. Yeah, that is then yeah. If you had used one single heat pipe, it would have become too long.
Yeah.
That is possible, but the heat sink is large enough to dissipate the entire amount of heat. So yeah, that is. Yeah. So by the way, this is just a representative design, because laptop design is not standard. Okay, it is going to vary from one manufacturer to another, within the same manufacturer, from one model to another, everything. Okay, so doesn't matter. This is just a representative one, unlike desktops where I think a lot of it is standardized. Okay, so what do I have to take care of? CPU temperature definitely is one of them. All the other temperatures, the graphics, in this case one of the heat pipes is running over the graphics, it may or may not. And now of course when you have multi-chip package or maybe CPU and graphics on the same package, so all those are possible. Okay, sometimes with a heat spreader, sometimes without a heat spreader. All right. So I have to take care of CPU. I have to take care of all the other components as well. Now, how are they getting cooled? I have just one fan. This fan typically in the laptop operates in an evacuative mode. There are pressurized modes as well, but most of them are evacuative modes. What does it mean? It means that the pressure inside the laptop is subambient. The fan is actually sucking in air. Through what? Through all the vents that you see on the bottom side, on the side, etc., except one which is this exhaust vent through which it forces it out. Okay. So as this fan runs, it will suck in air from all these inlets that is available to us, including your connectors and all. They are all teeny mini sources of air inflow, air ingress. That air, when it comes in, flows over these components and cool them down. And as I was saying, traditionally this was good enough. But however, now with more powerful memory, more functionalities and thinner laptops, etc., these are also non-CPU components are also becoming challenging. Okay, but okay, I have to keep those other temperatures, the component temperatures also within limits. Okay, you can see graphics and CPU have written TJ, components have written T case or TC, because many of these components are plastic encapsulated, so they are not at the junction. Okay, so for example, if I have a component like this, they will say that for the silicon the temperature is 100 degrees, TJ max is 100 degrees, that is where you have to keep it in. In the case, in a component like this temperature should be less than maybe 85 degrees. Okay. So during doing a testing here, I will put a thermocouple on top and make sure that the temperature is below 85, or even model also I will put a monitor point on the case. The assumption is that the temperature of the case is less than 85, the junction is also within its allowable limit. Okay. All right. So non-CPU components, what else? The exhaust limit, because remember this temperature that is being drawn in is at ambient temperature. As it flows over all these components, it is picking up heat, it is getting heated up. Then finally it comes to the fan over here. Okay, and finally it comes to this heat exchanger where it picks up the heat from the CPU as well, and in this case CPU plus graphics, and it comes out. Clear? So this exhaust temperature is much hotter compared to ambient. Now this temperature will also have a limit. Why? Because while operating a laptop, your hand may go there. You don't want, because that's an ergonomic limit. Okay. Now what is that exhaust temperature going to be? If Q is the total power, the sum total of all the powers, and I will call it, many a times it is called a platform power, it is going to be rho Q, where Q, this is flow rate or CFM, okay. Rho is density. So basically this is mass flow rate, Cp, which is the specific heat, times T exhaust minus T inlet, which is typically the ambient. This has to, because this is again from heat balance, first law. I brought in this volume, this mass flow rate of air at a temperature Tn. As it flew through as it traveled through this laptop, it picked up heat from this amount of heat from all the components, and by that and it heated up. So, this heat that is released or absorbed is equal to the increase in internal energy or enthalpy of this cooling air, and so this equation has to be balanced if I am assuming the entire heat is lost by the cooling air, right. So, what does this do? Now, I am saying that your ambient, I will design it for 35 degrees centigrade. This I am saying must not exceed, let us say 75 degrees centigrade. 75 itself is quite hot. So, what does it mean? It means that for a given mass flow rate of air, the total power that I can pack into this box is limited, and this is known as the thermodynamic limit. From first law of thermodynamics. Clear? All right. Now, you may ask, what is the big deal? Just run your fan at a higher flow, your flow rate will go up. Change the fan setting, run it at a higher RPM. Absolutely true, except that you also have this acoustic noise problem. Okay. So, this acoustic noise limits what is the maximum mass flow rate that I can have through this box, which in turn limits, given that exhaust temperature limit, the amount of power that I can have inside the system. This is the total power I am talking about. Okay. So, just want to mention here just a side note. Remember, I was saying that if you are using thermoelectrics or any refrigeration type of system, it is good to extract heat from a certain location, localized heat transfer, but finally what I am rejecting is more than the heat that I am removing, because the external work that I have done either in terms of electrical energy or mechanical energy is converted to heat. So, therefore, a system that is thermodynamically limited like this, like the way I have this equation I have written, if I am already at my thermodynamic limit, I cannot put a refrigeration based system. Okay. All right. And finally, last but not the least, the chassis temperature. Laptop should not burn your lap, a cell phone should not burn your hand. Okay. So, if you have to thermally simulate such a flow, lots of complexities, fan characterization, interfaces, heat pipe modeling. How do you model the heat pipe? Are you going to model this evaporation condensation? Oh man, good luck to you. But finally, what is it doing? It is acting as a very good thermal conductor. I will put an equivalent thermal conductivity that solves my problem. I do not want to get into the flow physics of what is happening inside. Representation of the heat exchanger. Many a times we do that we model the heat exchanger separately and then just put it as a as a heat sink with an equivalent thermal resistance. Yes, please.
So, can we back up one step to the heat pipe modeling? So, as you correctly pointed out before, if you have bends, then the effective conductivity comes down.
Right.
So, if you go to this particular model, it has a set number of bends. So, would you somehow scale your effective conductivity then in order to accommodate that?
So, what we typically do is, if this is, let us say this is a system, I will get this heat pipe and I will do some standalone testing, and I will measure the temperature here, 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 and according to the temperature difference I will assign equivalent thermal conductivities. Okay. Flow entrainment through connector points, I mean all these leaks and crevices, all this, your USB port, so these are all teeny mini sources of flow in flow ingress into the system, and we do not, I mean the more flow that we get, better it is. So, I do not want to neglect those, because that may hurt me. Okay. So, multiple heat transfer paths, etc., tortuous complex flow paths, and then you have all these cables and connectors running through. Are you going to model them? Good luck. So, we do not do that. Typically, most of the times what is done is you take a representative system, you put it to a wind tunnel, you find out what is the pressure drop, get an overall system resistance and put it in as a volumetric flow resistance. Otherwise, and you model it with a cable running in one direction and then the manufacturer gives you with the cable running in another direction. So, finally, you are not going to get accurate representation, not possible, because but this actually gives you a fair amount of, as I said, it is several what if scenarios. Where should I put the vents? What are the hot spots on the chassis, on the skin, on the components, etc. Okay. Example case study, this was one system. It's a laptop, and this is the bottom skin contour, this is the top skin contour. Top skin important because you are putting your palms, the palm rest temperatures are important. There are restrictions like There are absolute temperature limits for the palm rest. There are also temperature difference between the two, those limits. Temperature difference should not be more than 1 degree, because you do not want one hand to feel hotter than the other. So, there was one case, maybe I can say that after 7 years, not a problem, is back in 2010 I was trying to design some, and it was a delta T that was killing the design. Both the temperatures by themselves were within limits, much cooler rather, in one of the palm rests was much cooler than the limit. So, what I did was I took a simple metal plate and connected the two. So, basically I instead of I raised the temperature, I heated up something which was already overcooled, sort of. I was supposed to be a thermal designer cooling down stuff, actually I ended up heating because it was already cooled, and even if when I connected the two it was okay, all right. And then validation. So, this is a simulation, this is one case, simulation versus validation. You will never get exact match, but is it good enough? I would say at least gives you the contours overall. You can see wherever there are these vents. So, fan sometimes have vents. This was, I think, a hard disk door which also had some vents, and you see those places are cooler and the rest is hot. Okay. So,
any insights as to why the model, the hard drive in the model, hard disk in the model is so much hotter than?
No, this is an IR image. So, this
the
emissivity was different. Okay. Oh, there was also another thing. Sorry. The other thing is this one. When you have in flow therm and all, when you are having a hole, when you are having an opening, it is going to give you the temperature. Most likely this was the case. I mean, both of them. One was emissivity, the other was it gives you the temperature. It does not give you a real temperature in the sense that you model the bottom skin as an opening. You do not actually model the individual grills. So, it gives you an equivalent temperature over there, whereas over here there is no material, these are holes. So, it is actually reading something else inside. So, that is the reason. So, at the vents definitely most of the times it would fail.
Is this a solid state drive?
No, this was, I think, this is before solid state, this is HDD. All right. So, that kind of gives us kind of wraps up our discussion on modeling techniques. So, we started by saying that there are two types of models. One is the package level model where conduction is the main mode. System level model, you need to consider convection and flow, and those. So, therefore, the software tools you are going to use is different. I took the example of a laptop to show what can be the system level challenges. I showed some examples, but finally I again want to reiterate, validation is extremely important. Okay, otherwise nobody will trust our models. All right. So, with that I will end it here. Yeah.
The name you were looking for is Mentor Graphics.
Mentor Graphics, correct. Mentor Graphics, yes.
I want to have regarding this thermal thing. So, whether you will calculate that a person pulls the laptop from the lab, the heat, because it is evaporating, right? It sets up the heat on the human body.
Good. I think you will know better than me. When I was at the time I was leaving, and which is when laptops and cell phones were coming into being, many of us were actually telling them, not so much for the laptops, sorry, when tablets and cell phones were becoming popular, we were saying the human body, the hand itself acts as a heat sink. So, we cannot neglect that, but I do not know finally where it stands now, because well, you will have a better idea if that is being modeled. The human body is being modeled now when it is in touch, but very correct that you cannot neglect that, because especially for handheld products now and for thin form factors, that is becoming, that will be important.
Because that is from the day one for the handheld products, it is there. It's considered like how you are designing the shell over there to get the vents, to get the heat transfers and all those things. Handling device.
True, but do you model the hand? No, that's the thing. That's what I was saying.
They'll take some consideration.
Correct.
What my question is on the laptops, what happens is you have multiple vents. If you compare the handle to laptop has more.
Of course, much more complexities.
So, when you keep on the laptops and you keep on the lab, what happens? Your vents are closed.
Right.
And when the fan is sucking your it works in a sucking mode, right? It is not blowing mode. When it starts sucking, your temperature on your body starts picking up. So the heat will transfer from your body to inside, correct? And it goes through the fan.
Okay. Well, it depends on the what is the temperature.
It's like when you keep the laptop here, the ambient temperature what you are seeing here, the exit is here, the input is here. If the ambient temperature is at least, if it goes to 40, when it reaches here, it increases to 90, correct? Because
90, no, but
I'm just giving example.
right. Okay, it increases. Yes.
Okay. So at when the input is 30 degree, my temperature at my CPU it is 70 degree. When my ambient the input goes to 45 degree, this automatically increases. Right? So what I'm saying is, these are the vents, the input vents. When a person is holding on the laptop, lab, what happens is a person has a more temperature, like almost like 36 to 40 or something. The ambient is in the room temperature is around 25. What we consider as a room temperature is 27 degrees.
Okay, got it.
But the laptop is placed on the lab. The person's temperature is around 36. Whether it will be calculated when you do that?
No, typically.
Because that vents and all it is closed up.
Right, right. So I don't know, at least when I was doing it, it was not. The standard design procedure at that point was you place it on a table, and the table was also wood or something with some properties and with a 3 mm gap, okay, because of the standoffs, etc. However, the fact that the vents may get clogged when you put it on the lap, or actually we used to call it pillow proofing the design. Can we do that? And that was being looked at that point. Can we completely eliminate the bottom vents and only have it from the sides, so that even if you put it on a pillow on your lap, those are still open and the air can be sucked in. So there were some designs with that, and you can go and talk to Krishna Kumar Varadarajan, and he was looking at, I don't know where it stands now, but he had started to look at this pillow proofing techniques. It was mostly playing around with vent placements and all, not so much of any not any new thermal technology or so. But I don't know what the practice is today, but definitely a very valid point. And the other point I want to make is, depending on where you are putting in, let us say you are putting in the bottom skin on your lap is just below the memory. In such a case, probably the heat flow will be in the other direction, where the heat is going to flow from the computer to your skin. But there may be places where it can be the other way as well. Yeah, to put to summarize that long story is, at least till the time I know, and even of the papers I have read after that, it was not being considered. But if it's internally being considered and not in the public domain yet, I don't know. Yes, Sanket.
So what dictates the exhaust size? Because if we have a larger exhaust, then there will be higher dispersion of the exhaust hot temperature gas. So there will be a feeling of lesser temperature to our hand outside if we have a larger exhaust. So why don't we have a?
Okay. Why I'm on camera? Okay. No, it is a valid question. What dictates is, number one, aesthetics. Okay, what dictates is definitely it has to be as big enough for the heat sink, otherwise it's wasted. You don't want the flow to kind of converge after that. Thereafter, one is aesthetics, and the second is the structural strength of the chassis, because if you see the thickness is quite thin, right? And now if you have too much of porosity, then the mechanical strength is going to go down. And there is a third one which is not so bad, is there is also a limit on what should be if it is a jail bar grill, what is the thickness, and this, because there is a requirement, it is called an UL specification. I think they have a pin of 2 mm, right, and a 2 mm pin should not be able to go into because then it can short. And this we were trying to, at one point we were trying to argue. So they were putting this restriction on the vents also, okay, and especially for the exhaust vent, we were trying to say that, anyway the heat sink itself has that restriction. So if the vent is wider, what is your problem? Because it can go through the vent, but then it is going to get arrested in the heat sink itself. So, allow us to have the vent with larger gaps, so that my flow resistance goes down a bit. And that is when the mechanical engineers were pushing back and say, no, it is going to becoming too weak at that point, and if there is some kind of a compressive load, then it may crack. So that is what primarily it is. Okay.
So what if the thermodynamic limit and both the noise limit has been exceeded, or
then
has been reached to the whatever limit has been set, and still more power consumption is being done? So what of that?
Okay.
What will be done to that excess heat?
When you certify, you cannot have that situation. Okay. Once you have sold it, there may be such circumstances like that, in which case there will be customer complaints and all. But let us say the design phase itself, this is a continuous tussle between the electrical designers and mechanical designers. So, there is something called TDP, thermal design power, that is what dictates. Okay. Whenever people used to ask me, you are a mechanical engineer, what are you doing at Intel? And this was my favorite answer, what dictates the performance of a CPU? It is TDP. You know what does T stand for? Thermal, and thermal falls under mechanical. So, I dictate what this. So, that was my own feel good factor. Okay. So, anyway, so at that point I will push back and say, not possible, I cannot do it. It is not possible for given the size and the real estate that you are giving me. This is the best thermal solution I can have, and which is not enough to cool your system. So, you better basically remove some features or come up with a lower power design. So, this is what Professor Dasgupta was talking about. Till a long time there used to be this over the wall design, electrical designer will do it and then throw it over, now you go and fix it or figure it out how you want to cool it. But now it is more of a two-way traffic, where the design happens with both all the electrical engineers, thermal engineers, structural engineers, and even electrical signal integrity, power delivery, motherboard design, package design, CPU, VLSI designer. It is more of a teamwork that finally leads to a successful product. Okay. Any other question? All right. Sorry, I hope you are not too late for lunch. It's 1:20. We'll assemble back at 3.